day of ICAY 2026. I hope you all have had a great evening. And to kick off our program, it's an honor to present our keynote speaker, Professor Abdelmajid Ben Hida. Professor Ben Hida is a leading figure in African astronomy and the director of the Okimder Observatory. As a professor of physics and astrophysics at Cadi Ayyad University, he originally specialized in instrumentation and microelectronic before bringing that technical expertise to astrophysics research here in Morocco. He has played a critical role in developing our observational capability from characterizing the Acclaim city for the future extreme large telescope to advancing spectroscopic instrumentation. Beyond his own research in variable star and robotic telescopes, Professor Ben Hida is deeply committed to the future of our field. As the founder of the Okimder International School for Astrophysics, he is actively training the next generation of African astronomers, fostering international cooperation and leading the charge to preserve our dark and quiet sky. Today he will be speaking to us on Okimder Observatory, inspiring the next generation of astronomy. Please join me in giving a warm welcome to Professor Ben Hida.
Thank you, Aman.
The floor is yours.
Merci. Okay. So good morning. So before I begin, I will ask you one or two questions. So it will be interactive conference. So first, who was before use a robotic telescope or access to data remotely here in the public? Please raise your hand. Yes. 1, 2, 3, 4. The question: who was before use a robotic telescope who access to the data astronomy remotely? Data platform or yeah. Okay. And the second question, I want to know, for your vision, who is the most important instrument in the observatory? In the observatory, each observatory, which is the most important instrument in the observatory? Yeah?
It depends to the field. If it's space weather or it's spectroscopy or
for your field.
For my field, it's interferometer fabricator. It's the most important instrument.
Okay. And Babakar, for you? And for you, is it camera, telescopes? I don't know. It depends for each field, but
yeah.
Telescope, okay. Other proposition? Yeah. C'est une question piège, en fait. Yeah, I think that the question is the instrument, I use the instrument or asset, atu. So I think that the most instrument or asset in an observatory is pupil, is observator. Yeah, I think his pupil is and is young astronomer. So why I ask this question? Just here to explain you our vision in to develop Ukaimden Observatory. So, as you can see in this slide, yeah, our observatory in Ukaimden is more than observatory. We make it a place where researchers and future astronomers are trained. So, robotic astronomy that we use in Ukaimden Observatory, yeah, it's here to observe. Firstly, to observe sky, but the important goal, the important objective is about building capacity, sharing knowledge, and creating opportunity for future generations. That's what I will try to develop in this presentation. Okay, so my talk is divided in two parts. Firstly, I will introduce the Ukaimden Observatory, the contest and the infrastructure for research, and how we use robotic telescope for education. And I will talk also about international collaboration. And the part in the part 2, I will give an example for a small telescope to big science. How can a small telescope make a great achievement for research? And I will present a study case which spectrophotometry of variable star, and especially for a star earlier. Okay, so let's begin. But before, just let me introduce you our laboratory. It's called High Energy Astrophysics and Geoscience Laboratory, LPHAG. We have 4 teams, so 4 disciplines, 4 thematic: astronomy and space science. I think it's the main thematic. High energy physics and nuclear physics. Geoscience for energy transition. And recently, we add a new thematic transdisciplinary research team in educational innovation. So we are about 45 between research and associated research. And we have operated also, we have a master, which called High Energy Astrospatial. We have about 30 each year student, and about 20 PhD in 2027. And yes, it's the observatory that operate the laboratory that operate the observatory. So, but before I develop the infrastructure in the observatory, let me show you the key driver, how the astronomy are developed in Morocco. There's 3 key drivers. First, infrastructure. I mean, mainly the facility that we use in the Ukaimden Observatory. And yeah, in the Ukaimden we have many international collaboration with our colleague European, French, Belgium, yeah, many nationality, and Asian like Korean or Chinese and American. And the third K is that we organize scientific event like this Congress, ICAY 2026. And we have each year International School of Astrophysics of Ukaimden, which is called WASA. And in December in 2026, we have the 9th edition. Okay. Let me now introduce the observatory. We have officially inaugurated in 27, but we have begun the first, the first research about atmospheric and meteorology de l'espace for solar in the 80s. So before, 40 years ago. It's located in high Atlas Mountain, and the altitude about 2007. It's one of the best observing sites in Africa. Just to have an idea, when we compare with the Shaley Observatory from seeing the parameter that indicate the quality of sky is about 1. So it's comparable to observatory in Chile. Then Observatory is a strategic Moroccan astronomical infrastructure. But why this site is so exceptional? Because, firstly, high altitude. We have a stable atmospheric condition. Until now, we have a dark sky relatively. I hope that we continue. Low light pollution. We have more than 300 nights for observation. And so it's a strategic geographic position for global network. And so as you know, to make an excellent astronomy that begin with an excellent observatory set. That's the case for Oakhamden. Okay, let me show you the strategy of the observatory. Our strategy is combine research, education, and international cooperation with this single site. We hope that make our observatory a relay and platform for accessible to all African countries, and share with them our knowledge and our facility in observatory. So we use in education scientific research and STEM education, and we try to create a network of robotic telescope Africa that we have initiated in our Congress IFES, which organized in Marrakech in 2024. And hope that it will be developed. We have Senegal, Ethiopia, and mainly in Africa, as you know, is South Africa. So with them we try to create this network of robotic telescope. So to resume that, to summarize, is we try to combine research, education, and cooperation. All that make Oakhamden Observatory a hub for a scientific cooperation. In this photo, in this slide, we can say many countries that we have international cooperation. We have in America, North America, South America, Europe, Asia, Australia. So we try cooperation ever in the world. So in observatory in Oakhamden, we host an international research project, and we don't forget to develop South-South collaboration Africa. We try with Senegal, with Egypt, with Ethiopia, many Burkina Faso, to maintain this kind of relationship. Well, in this table, I present some most project, and we can, in the left, the name of project, most in French, and the year it began, and the thematic that develop each program. we have diversified program that diversified thematic until fundamental astrophysics to application. Yes, like surveillance spatial, surveillance objets au hasard. Okay, so yeah, and in the right you can see the country, all the country. We have Swiss, Croatia, Belgium, Spain, Russia, France, and also we don't forget. I will talk about that. The relationship between professional and amateur. It begins with and it begins with our national network of amateur astronomy. So we have a close relationship between professional and amateur in the observatory. Well, here you can see multiple photos showing instrument and platform supporting both research and application. Sorry, we have a pointer. In the right left, we can see Renoir for météorologie de l'espace. We have Korean program in the and TRAPPIST. And we have amateur as a telescope, and we have a future program which called astrograph telescope. I will develop this one by one, and mainly some infrastructure. Yeah, here. The Ukendon Observatory is hosting multiple dome and instruments supporting activity, so from fundamental research like variable stars to research to strategic space application, recently with space flux for space surveillance. I will come back for mainly to describe. I don't have time to describe all this project. You know, we have more than 15. So I will describe only the main 3 or 4 program. Okay. This image show you all a global thematic developed by each project. So we can see spectroscopy, photometry, astrometry for MOS and for AM, and that summarize many thematic that we develop through this diversified project. Well. Here I will develop, give you an overview of the major infrastructure currently operating at Ukendon. In the left we have a well. It's each program developed with Korean Space Agency and monitoring satellite and space debris for space citizen awareness. In the middle we have then the first project, a successful project. It's called MOS telescope for photometric monitoring of small body, and famous tools with Belgium University Liège, University de Liège. It's called TRAPPIST Nord, photometric monitor of exoplanet and comet. Well, let's begin by MOS. MOS for Morocco ICAY in the sky survey is a telescope which dedicates to monitoring a small body in the solar system. It has predicted more than 2 million observations. I will show you the last statistic in June, and it's internationally recognized. We can see quickly the main equipment: telescope 50 centimeter, and camera. In the detail of equipment of this project. Well, Here we summarize some main achievement. You can see for discovery, we have asteroid, near Earth, comet, education. So if you want to scientific highlight, we have operation since 2011, and more than 200 number asteroid discovery. And it make rank among the world's leading minor MPC observing station. We are about 20 in the rank of 20 in 2026. So this program at university is Base University Telescope make major contribution to planetary defense, solar system science, and also training the next generation of our student and globally young astronomer. The last statistical at in June this year, so we can see the discovery, last discovery for in we have 18 a number of objects. What I attract your attention about the total measurement. So we have more than 2 million measurement of. So it's a huge program. We would make a huge observation. So you can see the discovery in 2021, North Earth asteroid, discovered by Moss in 2011, and you're right. Binary asteroid discovered in 2018. Let's switch to the other major program, which can TRAPPIST for Transiting Planet and Planetesimal Small Telescope. It's a Belgian project with the University of Liège, and we have it's divided in thematic research, 50 for exoplanet program, and the other half and for comet and asteroid program. Main achievement, we have it operate for exoplanet, especially transit follow-up and system planet characterization, and for comet activity monitoring, international campaign. They work also for small body, and it's a very interesting program because it developed a program education, a program training for our student and Belgium student. So for each year we have a class of master in for 1 week, and they develop training for exoplanet and other thematic. So we can resume that a small robotics telescope can produce world-class science while inspiring and training the next generation for astronomy. A famous discovery for this program is the famous TRAPPIST-1, which the major discovery, which in 2017 by NASA, and play an important role in both science and education. For the first time, that we have discovered with collaboration with TRAPPIST South and NASA. Okay, I will just let me take 1 minute for this program because it's a model for a collaboration. Why? Because it's remarkable, because it made significant contribution to science, especially planetary science and astronomy. Groundbreaking discovery, example TRAPPIST-1, and advancing technology and education, foster technology progress and inspire next generation Morocco or astronomer. And spotlight on observatory of Oakenden. So we can say that TRAPPIST North demonstrated that with a small robotics telescope, 60 centimeter, we can produce a world-leading science while providing exceptional training opportunity for the next generation astronomy too. Recently, more recently, we have a new thematic in our laboratory. Yeah, we try in Camden to increase our contribution to space safely through space awareness with the program with the United Kingdom, which called Space Flux, and which is tracking satellite, thematic to tracking satellite space debris. It's installed now, and yeah, with the UK-based private company. So scientific output is high precision data, and yeah, and hope that in future we can make training in space surveillance with our strategic impacts. This range of observatory position in this new field in our observatory, in our laboratory. Okay. Yeah, a very interesting program because which in the round table we have discussed the role of amateur to contribute to science in astronomy. So we have developed this collaboration with the national association astronomy, and with height, which can, a partner which called Height Atlas Window of the Cosmos, HAWC, in Morocco. It's a group of astronomers Moroccan has developed this company, and they have put their equipment, as you can see in this photo on the left, and they are very, very active in the observation, and they help us in our campaign, like recently with make observatory for variable star and make data for photometry for variable star. So they are very active and they help us in many fields. So they also training opportunity for Moroccans in observation astronomy survey. They promoting astronomy and the public engagement in Morocco. So yeah, so it's very interesting, and we continue to develop this kind of program. Well, until now I show you the side of research. Let me now about thematic is how to use robotic telescope in education. So why are robotic telescope becoming important in astronomy education? Because with robotic telescope we have continuous and remote access to real astronomical data. We learn the learning approach is remote to develop remote observing session, and in the real access to real-time astronomical data, we can persist a maximum of students worldwide, and you can train in modern astrophysical techniques. So we can, with all students, to do real science. Okay. The role of robotic astronomy allow us to access, as I say, to real astronomical observation, to make training in data analysis. Participate worldwide, making education more inclusive, and develop scientific skills. So students move from theory to practice with this kind of data. Yeah, because it's been with robotic telescope. How? Which activity can we learn with students with robotic telescope? We can image processing and calibration to prepare astronomical data for science. In Camden, we use photometric and spectroscopic measurement, for example. We can, with photometric, analyze light curve analysis, and after reduced data, we can astrophysical interpretation to understand the phenomena of it. So, with robotic telescope, we can develop scientific skills. It's the goal of that we use it. let me, to illustrate that, I show you some photo that from training, and that we use some data from our student in University Cadi Ayyad, and a colleague from Senegal, Salma, which make his training in observatory Cambridge. So regularly we organize session training here with the international student in March 2026 from University of Liège. You can see the snow in I think in March, in the beginning of March. This year is very special, and we have maximum of snow this year. So I think this the students have enjoyed their stay in Ukimden. Well, so that to say that we can, with robotic telescope, make many training for our students and for international students. Also, we can sorry. Also, we can organize an international workshop like that in October. I think in October 2026. No, 25. We have in this workshop, an example for this workshop, we have organized between a student in Senegal, Morocco, Egypt, Belgium, and Emirates. Yeah, and we have a session training. We have used the data for platform, I think, Mohammed Kepler. Yeah, so this is a kind of training that we can make in our university. Also, we can use the data and to train in teacher. We make regularly with the teacher of secondary. So we make some session training to in astronomy education for integration of astronomy in STEM teaching, and we make practical activity. We have also do in, I think in 2022 practical activity from astrophotography. Well, now let me switch to the educational impact for the use of robotic telescope and data. As a result, with that we improve scientific literacy. We increase student engagement.
Recording stopped.
We access to real astronomical data, and so to the main is to develop scientific vocation and the career for young astronomers. Well, but yeah, we will do. Yeah, it's beautiful. It's wonderful to have a telescope robotic, to have data. But each in each observatory we have many operational challenge, like network connectivity. Yeah, you have a challenge with the DB. We have the high altitude constraint. Affecting maintenance and operation. And for example, for this year, when we have a lot of snow, we have many problem with that. Another challenge is telescope scheduling for multiple program. Yeah, when we are many, so for some, to have scheduling for each one. And strong international coordination for optimal to use facility in Okenden. Well, the solution for this challenge, we try by automation system to use to remote operation platform for maintenance, to use regular maintenance strategy, answer the reliability and long-term performance of the equipment, and yes, sometimes the international collaboration from all supported data sharing, sorry, and efficient to use of facility. Well, yeah, I talk about voluntary support. It's very, very important because the development of, needs this support to strengthen scientific infrastructure and observation capability. The most example is the Okemden facility. Promote teaching, training, and STEM education, like this event, when we meet other specialists from all the world. So, enhance international cooperation and partnership. I give you some examples that we have. That Valerius is a program project Belgium. We have make many proposal for European program like Materna, Astronomy. I give you an example. For this one, we more than 15 countries in Africa. So we make one proposal, and I think with some partner, Belgium, Italian, and Spanish and French partner. So this kind of international collaboration help us to support astronomy education and in observatory. Well, so when you develop scientific collaboration, naturally you lead an international scientific event like this conference. So we have, for example, this ICAY, but we have organized before ICAY, for Astronomical Society, African Astronomical Society Conference in 2024. And I think for in the same year, we have organized to the International Yearly for Variable Star. And unfortunately, Morocco is the only country, African country that belong to this community. And for the first time in Africa, we have organized this kind of event for Variable Star. So we can then help to connect African astronomers with the community, with international community. I take your attention that we try in each event that we have organized in Morocco, in Marrakech especially, that invite the maximum of our colleague and student African. But we have many challenges, and mainly is funding and yes, to have mobility. Because we offer all, I think we always offer this day, but the challenge is to have a funding to travel. It's the main for African student and for African partner. Well, we also organize school, international school, like we have organized WAZA and Fourth Arab School for Astrophysics in 2019, and we have stellar physics in 2024. So we try to diversify the thematic, like for example, for this year, there was a school in December. We train many thematic, and for the first time, a new thematic that we try to develop is radio astronomy, and we will invite some specialists and try to develop this new thematic in Morocco. Well, I can't forget the outreach program in parallel that we make around which we use facility of observatory. So the use of Camden Observatory to observe facility for training STEM and education for teacher and student of the secondary. We organize observing night in Camden. We have each year which called a festival of astronomy of Marrakech. Each year, I think is the 21 edition this year, or 22. And so we try to share a beauty of universe. Is one of the best way to inspire future. Here you can showed our engagement in rural with young rural girls in the make some session of outreach with young rural girl in this association, which is called Dar Taliba. We have many Dar Taliba in Morocco, in Marrakech, in the rural region too. Well, we organize some conference online to inclusive astronomy with astronomy feminin, Dar Taliba stars. So usually we use this kind of event. So we try to develop with all people and share all people the astronomy and astrophysics, the beauty of the universe. So now what we want to try in the perspective, we want to normally to expand our robotic telescope network, especially in Africa, to integrate all driving education tool, growth of remote learning opportunity, and strengthen astronomy in Africa through collaboration, training, and capacity building. Well, to summarize this part, we try to democratize access to research and education, expanding educational opportunity. We support capacity building, research and education. So hope that can inspiring the next generation of astronomy. So I can try to say that robotic observatory, like Camden, are not only scientific instruments, they are powerful tools for education, collaboration, and inspiration. So it's the end for the part 1, and let me switch to part 2, and to talk about one program that developed in Camden about to study variable star, and especially make spectrophotometry of variable star at Camden, Boston. We have automated telescope. We make remote observation with this kind of telescope, and you can see the dome of. You can see tomorrow. In the main dome, we have two telescopes. One is dedicated to photometry, and the other one is to spectroscopy. And we have a small spectrometer with resolution 12,000. I will develop quickly this equipment. So tell you about why we choose to study variable star, especially auroral layer. So because they are standard candle. They allow us to measure distance with Milky Way. They help us to trace in galactic structure. They probe an ancient stellar population. And they are a very laboratory for stellar and study evolution, stellar evolution. And they are tools for cosmic calibration. All that things make us to motivate to study this kind of variable star. Well, now let me tell you about the method that we use to study the variable star. We use both and spectro and photometrics measurement. The objective for the study is to probe the dynamic of pulsating star atmosphere through high-resolution spectroscopy and precision photometry. Our approach, when we make photometry measurement, it's to determine pulsation period and light curve variation. And for spectroscopy measurement, we determine radial velocity, line profile, especially hydrogen, helium, iron, and atmospheric property. So we have photometry, we have spectroscopy, so we combine, analyze, and try to provide a comprehensive view of stellar pulsation. In our analysis, after for data, we focus for shockwave propagation, metallic line doubling, study emission or absorption for hydrogen and helium. So we can allow us to understand some mechanical and thermal structure of the atmosphere. With all that method, we try to advance astroseismology by improving our understanding of physics of auroral pulsation. As you know, before I will show you the material quickly. You can say we have a small telescope. It's 16 inch, so about 40 centimeter with camera, with mini camera. But a shell spectrograph, which covering a range, a spectral range with 4,000 and about 7,000 angstrom. And we have equipment to calibrate flux and wavelength for spectra, spectra. As you know, that variable star is a star that pulses. And the pulsation comes from an instant balance between gravity pulling inward and pushing outward. Here you can see a typical light curve for a variable star. So in the bottom you can say the state of the star when expansion and contraction, and related to the intensity of light curve. Okay, and we have a periodic phenomena which is periodic. So more than pulsation, the variable star, they have an intriguing phenomenon is which called Blaschko effect. A Blaschko effect is an effect which saying when we have a moderate intensity, we have a moderate in intensity and variation moderate in phase. So I'll give you an example. For IRL star, we have an effect Blaschko for about 40 days. And we can see here the variability of the maximum in light curve and in the phases. Under about 9 days. So when you try to observe this phenomena, you have to make simultaneously minimum 40 days observation, so 14 night observation. To the strength, to real strength of our project comes from combining space and ground-based observations. So we combine the photometry and spectroscopy data with space mission data like Kepler with Kepler mission and test mission. So, for example, the Kepler mission is a mission between 2029 and 2018. The objective is detect Earth-like exoplanet study stellar variability, okay, and provide data on variable star, and test the launch in 2018. The objective is discover exoplanet, namely star, and observe also stellar variability. We have an example in July 2019. We have make a simulated campaign with tests in July and August. I think August, and we have a test mission about 27 days. and have make in our observatory simultaneous observatory, photometry, and spectroscopy. So it's a very special occasion to combine this result and to have more information about the state of atmospheric in atmospheric stellar of RLR. Well, so about space-based observation, we have high precision photometry, more than observation in ground, like Camden, because the rapport signal noise usually in Camden is about 30, which is weak. So you know when you reduce your data, it's very to observe some special phenomena. It's very hard. So spectral survey with Gaia. The benefit of space observation: reduce noise, continuous monitor, find star observer, enable discovery of subtlety of variability for study astronomy, and with the combined space and ground data for robust modeling of stellar interior and evolution. Well, here you can see the result for platform, space platform and Camden, and we can see the noise and signal rapport of noise, and we can we have Kepler result for Kepler, TESS, Camden, and GEOS. I think in this our colleague in Marseille, they make this observation. So so we can for Kepler, for example, we can see the modulation of intensity and modulation in phase, which making clear that we have Blaschko effect. Yeah, we can see that. Yeah. Now, come back for our result ground. Here we can see an example of image CCD exposed with A-shell, our spectrograph. In the left is a brute spectra. I miss spectra, typical spectra in the right, because PDF. The spectroscopic data we using the free and open source Astronomy Au-delà, while photometric were processed by IRF. So now what we can learn with when you have spectra for young astronomer, we can detect, determine temperature, pressure, radius, luminosity, chemical, many information that you can, if you have reduced your data, So all this show you a spectrum behavior, typical, with emission line, continuum, absorption line, and So let me go back to our study for RLR. We focus especially for some signature like hydrogen, helium, iron, and you can say the wavelength corresponding. So we have made an anti-monitor campaign since 2015. And we continue to make this campaign to study variable star. We focus on doubling fire and metallic line to try to understand the motion of the motion of different layer in the atmosphere. 3H alpha emission. We have 3 emission H-alpha that we have detected in our spectra. So, spectral signature confirmed the strong coupling between shock waves, it's our result that we have, and atmospheric dynamic. So, when we make campaign for a lot of months, a lot of years, since we have begun in 2014, so we have a lot of data. So we have make a new Python interface with a doctorand USF Python, So yeah, pattern interface for our spectroscopic data, which help us to analyze quickly when you have a lot of data to reduce. So we can, I can give you an example for when we want to plot many results from month and year. An example here that of our result, which showing the evolution of an example spectral profile of hydrogen and helium in our pulsating star RLR. In the left we have helium, and in the left, helium, and the right hydrogen. We can, it's this weak structure is very important to give you a lot of information of the motion of the layer and how the evolution of the atmosphere of this variable star. So we observe phase-dependent light burden in H alpha and helium line, which indicate shock probably to atmosphere. A different way to visualize this evolution is to plot the 2D program. This figure illustrates the evolution of hydrogen spectra. They are changing, and the red color is mentioning the emission, and the blue color, the blue one, is absorption. Well, I have time, 3 minutes? So yeah, I have 2 left. So just, let me show you this slide. When I compare that we can make big science with small telescope, and I have compared our telescope, our observatory, with this one in Hawaii, which diameter we have. So we have compared in the left our with 11 pouces, and for Hawaii is 3 meters. So we can see in the left who came then the spectra to they obtained, and in the right from Hawaii. What I try to explain to demonstrate is, if you have a small telescope and a good site like observatory, we can make a big we can compare to big observatory like Hawaii. You know, in the left we have only 20 centimeter, and in the right the main they allow us for the first time that we have observed. They can't observe it in Hawaii, but we have observed in for the first time the second apparition of helium was detected using a telescope for 45 centimeter. So to summarize this party, our spectroscopy observation provide a new insight. So insight in the atmospheric dynamic, pulsating star particularly, and also I show you that with small and medium-sized telescope we can deliver high-quality scientific results, and we can combine group-based spectroscopy with space-based photometry. This synergy is essential for comprehensive understanding of stellar prediction. And we conclude with a general conclusion that our talk, my talk. So, I hope that I can have show you how those who can then inspire the next generation of astronomy by providing access to world and class research, by using robotic telescope, international scientific collaboration, and training future scientists hands-on experience with professional astronomical facility, remote observation, and real scientific data. And finally, building an international scientific community like this aujourd'hui, connecting Morocco with Africa and the world, sharing knowledge to school, conference, outreach, promoting diversity, collaboration, and scientific excellence. Okay, thank you very much.
Thank you, Professor Mjid Benhida, for this inspiring talk and for your continued dedication for advanced African astronomy in Africa. And we have a few minutes for the questions. Is there any question there?
Hi. I have a question. The question is, I don't know if you control the statistics about air quality here in the observatory, but I would like to know how many nights do you have or observation in a whole year?
Yeah, initially we have we make measurement of seeing, and I think we have really in the beginning we have more than 300. Yeah, but I think really now I think that's decreased, but yeah, but still yeah we have a lot. Yeah, we have. A lot of night to observe. Okay. Yeah. But when the sky, we have, as said to you, that we have a compare seeing, you know, seeing is a parameter, yeah, like Shaley or the great observer in the world.
Okay.
Yeah. So that make us to can observe like. Thanks to this condition. Okay.
Hello, I'm Ines and I'm also working on seismology. And I had a question. Are you thinking about studying other types of variable stars, or are you only focusing on RR Lyrae?
Yeah, we have the main campaign is for RLL, but we have make campaign for RSQT. RSQT. We have a period for 140 years, 40 days. So yeah, so we have choose a little period and medium period. But if you want to, if you have an example, want to study, if you have a variable star, we can do it. We can do it. The company. Yeah, because we are limited in magnitude. I think to. It's with spectrograph, mainly spectral with nine in magnitude. So
okay. Okay. Thank you.
Thanks for this presentation.
Yeah.
So in this presentation, you say you use spectrophotometry as fundamental methods.
Yeah.
Photometry. So do you use another fundamental methods like polarimetry or spectropolarimetry?
We use.
Do you use another fundamental methods like polarimetry or
no? With the polarimetry, we have to have a lot of flux. Yeah, we need a lot of flux. So with the maximum, say 40 centimeter, I think it will be very difficult, or choose a maximum magnitude. But yeah, so but we are limited. Yeah. So we have tried to do that by splitting. But yeah, I think the max current is the magnitude. Yeah. So I hope that we will have with the great diameter that you can make like polarimetry.
Good morning. My question is, how do you face light pollution in Oakhampton, and how you keep face light pollution in Oakhampton? How you keep the night sky clear?
Well, until now we don't have any light pollution. I hope that we will continue, but when we reduce our data, we can make some. But no. I hope that we continue. It's a very challenge. We have we try to make a reserve, a dark sky reserve. We have a project for 80 kilometers around the Oakhampton Observatory. But with I think the challenge is with new project, tourist project, it make very, very difficult. But hope that we have until now. I think mainly the main pollution light is a village. Is the village, but we try to discuss with them, and they are understand. So yeah.
So first, I would like to say thank you for your speech and for your time. And my question is about the Blasco effect. Yeah, my question said, is it always take 40 days, or it depends about the star and or about the planet that you're studying too?
Yeah, sure. It's a very good question. Yeah, it's depend. Yeah, I give you especially for this star, RLN, which make 9 days, about 3 days. It's variable, but a little for the same star. Huh? 1 day, 2 days, but I think for other it's depends for period. But the intrigue phenomena, which is Blasco effect, is they have a lot of explication, but until now we don't have the sure explication. So yeah, I think the last and significant explication for Blasco is the wave shock. The shock, yeah, to explain with the shock, the shock waves in the atmosphere of star of RL. Question?
Sorry, but we don't have much time for the question. You can continue with the discussion in the break cafe. And for now, we will move to our next talk.
You.
I will welcome.
I have just one remark, not a question. Since you mentioned like the events that we organized in 2024, so you forgot one important event where we've made like significant effort with Dr. Anders and Georgi, which is the ICAY Symposium in 2024 in August in Cape Town. That were. Ah, yeah, okay.
Yeah.
But it was like international conference, that's why I said that.
Very important that
Yeah.
Professor Jamila mentioned that we have
Thank
forget
you.
to mention a very important event which make in EAU in Cape Town in August in Cape Town. We have the symposium of exoplan with Professor Andy, and we have also focus meeting of robotic telescope that we made. So yeah, it will be a great year in 2024. We have about how much? Six events in 1 year. Yeah, yeah. Thank you very much.
Thank you, Jamila, for the question, and thank you, Mr. Abdelmajid Belhida. And now I will just inform you that we have a small change in the program. We'll start by Ahlam Lotfi. Next we will say the talk of Walid, and then ENS, and we will finish this morning session by Yasin. Now I would like to invite the Ahlam Lotfi. Ahlam, yeah. Ahlam will present a comparative astroseismology for an irregular star. أحلام أحلام لطفي لا أحلام سليم.
أحلام, the floor is yours.
Go ahead. Thank you. Good morning, everyone. First of all, I would like to express my sincere gratitude to the organizing committee for accepting our work and giving me the opportunity to present our research today. My name is Ahlam Lutfi, and I will be present our comparative astroseismologic study of RR, focusing on its pulsation, dynamic, and Blasco effect using combined space and ground-based observations for Kepler test and Oakenden Observatory. To get this talk, I divide my work into four main sections. First, we will review the nature of RR Lyra stars. Second, we will look at the Blasco effects and its frequencies. Third, I will present the three observation instruments, Kepler test and the Oakenden Observatory. Finally, we will compare the results and discuss future perspective. Let us begin with a fundamental concept. Stars are extremely far away. We cannot touch them. Light is our only message. By studying how light changes over time, we can understand the internal physics of the stars. This field is photometry and astroseismology. There are two types of variable stars. Intrinsic variables, the lights change because of outside the star. For example, another star pass in front or thus blocks the lights. The second is the extrinsic variable. The brightness change because of outside stars. RR is an intrinsic variable star. It passes from inside. Now let us introduce Lyra. It is the prototype of RR EB pulsation stars. It's an old pulsation true stars and on the horizontal branch in the diagram HR. Its brightness change periodically due to radial pulsations. Its fundamental period is about 0.566. However, the pulsation is not always simple. In many RR Lyra, we observe the Blasco effects. This is a long-term modulation of amplitude and phase. For RR Lyra itself, this period is around 39 days. In the frequency domain, it creates side peaks called multiply. Understanding the Blasco effect is still a major challenge. Several physical models exist. The magnitude field, non-linear resonance, convective model, and dynamic choke model. To test this theory, high precision observational data is necessary. We can observe the light curve of the stars. We measure two main parameters. period, which is the time for one full cycle, and amplitude, which is the brightness range between maximum and minimum. To extract physical information, we perform Fourier analysis. We identify the fundamental frequency with the period 04, F0 near 1.764 cycle per day. We also observe many harmonic frequencies like 2F0, 3F0 and 4F0, etc., which reflect the sinusoidal shape of the curve. To extract physical information, we perform Fourier analysis. We can observe the peaks appear around the fundamental frequency and his harmonic. In this work, we compare three data sets. Kepler with long continuous space data, 127 days, TESS with height 2 minutes cadence, 27 days, and Oakenden Observatory with ground-based follow-up 14 nights. Our methodology inside data cleaner like light curve analysis, pre-weighting using period 04 and frequency interpretation. Frequency is accepted if signal tremors is greater than 4. Here are the light curve Kepler for cadence 1 and cadence 2. Thanks to Kepler long Baseline, the slow amplitude modulation for Blaschko effect is directly visible in the time domain. For the fundamental frequency F0 is measured the 1.764 cycle per day. The spectrum display numerous harmonics proving the highest precision and resolution Kepler. Kepler clearly reveals the Blaschko effect signature. We observe symmetric side peaks around the main frequencies. From this triples, we derive Blaschko frequency FB of 0.02 per day, corresponding to a Blaschko period of 39.4 days. Next, we analyzed the test sector 14 days. The sampling test recording more than 1800 points with 2 minutes cadence over 26.85 days. The sampling of individual cycles is excellent, but the baseline is relatively short. We test period 04, find a fundamental frequency F04 1.764 cycle per day. Harmonics are detected at up to 21 F0. However, because the time baseline is short, the resolution is around 0.037 per day. Therefore, therefore, no Blaschko multiply could be resolved. Now, the observational contribution of this work, the ground campaign at Oakenden Observatory, we used the Hawk 15 telescope and ASCAR FR A 402 camera and a green filter with 10-second exposure time. The Oakenden campaign covered 40 nights over 59-day window, collecting 6,579 points. This data set represents a substantial effort for ground-based monitoring. The Fourier analysis of Oakenden data gives a fundamental frequency F0 of 1.1764 cycles per day. Harmonics are significant up to 6 F0. The total observed peak-to-peak amplitude is 1.291 magnitude. In the folded curve, we observe cycle-to-cycle dispersion. However, ground data suffered from daily gaps and atmospheric noise. No significant Blasco frequency meet our signal-to-noise criterion. Those dispersion alone does not confirm a robust frequency detection. Comparing the three instruments shows the excellent agreement for the fundamental frequency. The difference between Kepler and TESS and Oakenden is extremely small, order of 10⁻⁴. This confirms that ground observations can accurately measure mean periods. Regarding harmonics, Kepler offers height, thickness, and multiple resolution. TESS reach very high harmonic 21 F0, but lacks baseline needs. Oakenden reaches 6 F0, limited by ground basic noise. In summary, Kepler resolved the Blasco effect thanks to continuous long baseline observations. TESS and Oakenden cannot confirm it. Currently, no detection in TESS or Oakenden does not mean the Blasco effect is absent. It is limited by duration and sampling gaps. In conclusion, first, the fundamental precision of RRA is consistently recovered across space and ground data. Second, Kepler remains the gold standard for resolving fine Blasco structures. Third, duration, continuity, and noise are the critical parameters for detection weak signal frequencies. For future work, we propose 3 paths. First, expand ground monitoring over multiple seasons with multiple site networks. Second, combine photometry with spectroscopy and O-C diagram. Third, prepare for Plato mission data to study long-term modulation with high precision. And thank you for your attention.
Thank you, Ahlam, for your presentation. And now, are there any questions here?
Thanks for the presentation. So I work on the same topic in my master degrees. So can you explain the power whitening method used in period 04, like to extract the fundamental periods, the satellite and his harmonics?
D'accord. Je vais répondre en français, pas de problème. Pour le logiciel période 04, il essaye de faire une analyse fréquentielle pour bien visualiser les détails autour de la pic fondamentale F0, de la fréquence fondamentale F0 et les autres harmoniques. Ce n'est qu'une transformation de Fourier pour bien visualiser les très petits détails de l'effet Blasco. Thank you, Ahlan. And that brings us to our break. So we will pause now for 20 minutes and be back at time to so we can resume our session on time. Thanks. please, we will start. Monsieur, بنا بدأ. على جميلة جميلة. الحمد لله. Welcome everyone, and let's get started with the second part of our morning session. I will like to invite Wally to present her presentation about the spectroscopic analysis of variable stars. Walid, the table is yours.
Hello everyone, my name is Walid Aitleh Passia. I am master student at University Cadi Ayyad, Faculty Sciences Civiliya. Today I will present our work on the spectroscopic analysis of variable star, especially propagation shock wave in RR line. This work was supervised by Professor Abdelmajid Ben Hida. First I will begin by defining variable star. The variable star are star whose brightness variation are detectable on a time scales comparable to a human life. We distinguish two types: variable extrinsic and variable intrinsic. Variable extrinsic, whose brightness variation due to external phenomena such as eclipse binary and rotation variable. Variable intrinsic, whose brightness variation due to internal phenomena such as cataclysmic variable and pulsation variable. This diagram summarizes the classification of variable star. As we can see, variable star are divided into groups: intrinsic, extrinsic. Extrinsic include in two classes: eclipse binary and rotation variable. Intrinsic including pulsation star and cataclysmic star. In this presentation, we will focus on the RR Lyrae, which are pulsation star, meaning that expand in the and contract during pulsation cycle. Now, why do RR Lyrae pulse? This is explained by the kappa mechanism proposed by Edencon. So why do RR Lyrae stars pulse? This is explained by the kappa mechanism proposed by Edencon. During the contraction phase, the radius of the stars decreases, which causes the density to increases. This increase in density leads to increase in opacity, meaning the other layers become less transparent to radiation. As a result, the radiation coming from the core gets trapped or blocked instead of escaping. This trapped radiation builds up pressure, which eventually pushes the layer back outward. This marks the beginning of the expansion phase. The radius increase, the density decrease, and consequently the opacity increase as well, since the layers become more transparent again. The trapped radiation is finally released. This release of energy causes the stars to lose the pressure that was pushing itward. So it starts falling back inward, and the cycle begins again. But that dispensation is not perfectly smooth. It's actually generated two shock waves within atmosphere. The main shock and early shock are described by Hill and Foucault. The main shock results from a sudden halt of the infilling photosphere, followed by immediate outward expansion. The early shock results from collision between atmospheric layers during the unfold. To study these shock waves, we use two observational approaches: photometric analysis and spectroscopic analysis. In this presentation, we focus only spectroscopic analysis. To study this shockwave through spectroscopy, we focus on three spectral lines. First, the hydrogen emission. The hydrogen emission, which is the main tracer of shockwave in the atmosphere. The second, the helium emission, which only appears the shock is intense enough to excite this helium. And third, the iron line, which shows a particular appearance and disappearance phenomenon that we will also analyze. Let's start the first appearance of H alpha. This figure shows the duty profile of H alpha as a function pulsation phase. The horizontal axis we have rest frame velocity. The vertical axis we have phase. And the right side we have the color scales represent the relative intensity. At phase 0.9, we observe a blue shift emission immediately followed by the absorption lines. This is because the main shock generated by the kappa mechanism we described earlier reaches the line forming region at this point in this pulsation cycle. As the shock passes through, the shock compresses gas begins to emit in H alpha, and this emission moves outward, which is why it appears blue shift. Meanwhile, the doubling of the absorption line reflects the coexistence of two components. The layer is already reversed by the shock moving outward, and the layer still falling inward, which haven't yet been reached by the shock front. The second appearance of H alpha. This figure shows the spectral profile of H alpha at phase 0.7 with wavelength represent the horizontal axis. In the vertical axis we have relative flux. We can see a deep absorption in this figure at end just before it indicated by the arrow a small emission. This weak blue shift emission marks the arrival of the early shock in the line forming region emits in H alpha as it moves outward. The third appearance of H alpha observed at phase 1.2. We can see a weak redshift emission indicated by the arrow appearing just after the main absorption line. This redshift emission marks the expansion of the atmospheric driven by the main shock, a signature commonly associated with expanded gas. This figure shows the evolution of the H alpha line profile when the main shock wave propagate in the envelope of any RL line stars. from the early stage, from an early stage to a late stage. In early stage, around 0.9, the shock is still closest to the photosphere. This emission is blended with absorption. This gives the doublet profile, as we can see. And late stage, in the phase 0.3, the shock has moved further away, forming a detached expanded shell. The emission and the absorption are now clearly separated, forming a Cygni profile. Let's pass of helium N. This figure shows the evolution of the line profile at different phase. We observe this figure in the first graph, the second graph, and the third graph, and the fourth graph. This emission is the signature of a strong hypersonic shock, intense enough to also excite helium, unlike the weaker shock, which only product hydrogen emission. Let's pass for iron. This figure shows the profile of the line for three different observations. This appearance and disappearance phenomenon is directly linked to the passage of the shock wave. As the shock compresses and heats the gas, the iron absorption temporarily weakens or disappears before reappearance once the shock has passed and the layer returns to its normal state. We observe this pattern consistently across all three datasets, confirming that this behavior is a recurring signature of the shock propagation in the atmosphere. To conclude, shock wave play an important role in RLI star. They modify the atmospheric dynamic of the stars, driving successive phase of contraction and expansion. This shock also leaves distinct spectral signature, including the appearance of emission line in hydrogen and helium, the doubling of absorption lines, and the appearance and disappearance phenomena observed in iron line. Studying this signature allows you to trace the propagation of shockwave through the stellar atmosphere, and you better understand the pulsation mechanism of RR line.
Thank you, Yassine. Thank you for presenting. Thank you, Yassine, for presenting such a practical tools for our community.
Thank you.
Are there any questions there? No questions. So we move to the next presentation. I would like to invite Ines and Miss Toy. She will present the modeling of oscillation red giants banyers.
So, hello everyone, my name is Ines Amostoy, and I'm very glad to be here today to present the subject of my master thesis that I conducted in the Canary Islands in Tenerife last year. So I'm talking today about finding the sweet spot, and I'm going to show you how I modeled an oscillating red giant binary. So it's not actually binaries, it's a bit of oscillating stars. So I'm mixing a bit what we said over the past few days. So first of all, in astrophysics, one of the big questions is to determine the age of the universe, of the things that surround us. And in order to do that, the light of the stars are the main thing that we can measure and study. So the mass of a star, the age of a star is highly reliable on the mass of the star. And it's very important in many domains of astrophysics, for example, the galactic evolution, and also the exoplanet characterization, because when we want to study an exoplanet, we basically study the light of the star, and the better we characterize it, the better we can characterize and constrain the parameters of the planets. So I'm talking about mass mainly today, so let's give a definition. Actually, I will give two of them. The first one is the dynamical mass. It relies on the orbital mechanics, so Newton's law, Kepler's laws. So there are two main advantages. It's highly variable when the orbit is constrained, and also it's independent from any stellar models. But since I mentioned an orbit, it's only applicable to binary stars, so we reduce a lot the sample of stars that we can study. Then the second definition of a mass is the seismic mass. So it relies on the astroseismology, so the study of the oscillations of a star, and it's applicable for all low mass stars, and it's independent from the inclination, so we can see it doesn't depend on that. But it's highly dependent on scaling relations. I will come back to this later. And we need long-term series data, continuous if possible, so it's quite complicated. So now that we have two definitions, let's compare them. So here in this plot, when we see the astroseismic mass and the dynamical mass, we can see, let's say, three things. So the first one is that there is discrepancy between both definitions because the stars are not aligned on the y=x axis. The second one is that we tend to overestimate the seismic mass compared to the dynamical mass. And the third one that you can see is that the sample is very, very reduced. So you may wonder why. Actually, it's because the stars that were on this plot were very characteristic, very specific. They have three main characteristics. First, they are double-line binary, so on the spectroscopic spectra, we can see the fingerprint of both of them. Then they are eclipsing binaries, so we see them edge-on. And then one of the two components, at least, presents stellar oscillations. So from these 15 benchmark systems, the project of the internship was to add a new one. So this is the star I worked on. I'm going to call it EDFX from now, way easier. So let's move on to the literature. It has been discovered 3 years ago by Gaia. It was on the DR3 release. And the data gave a period of 3.8 days. But we can see here that even if we have 3 filters of Gaia, the data is very sparse. We can do much with that. But TESS comes here to rescue us, and it gives us this normalized light curve. So here we recognize two transients. We see that the orbit is well covered. The sample of the test data is good. So this binary system is composed of a red giant and a companion star. We don't know yet what is the companion star. It's probably a main sequence star. We don't know much more than that. So basically the first eclipse that we see here is when the red giant is in front, and the other one when the companion star is in front. So this is what we have only from the literature. Then I started my work by using spectroscopic data from Las Cumbres Observatory. So this is basically a network of telescopes all around the world. And I, for these targets, used only the Chile Observatory and the South African one, because it's a southern target. So here is the first task that I had. It was about testing the LCO data, if we can trust it, how much we can trust it and everything. So I studied the wavelength stability and also the radar velocity one. So we can see that the sigma that was given by the spectra is way smaller than the typical binary amplitude. So the answer is yes, we can trust this data. So what do we have on the data set that LCA gave us? There was also the spectra and also the cross-correlation function. So it's a widely used method on radial velocities. It consists in taking one observation, so one spectra, and another one which is a reference with the star at rest, where we know the temperature or the parameters, and then you will measure the similarity between both. So you shift, for example, the reference one, and when you get to the maximum of similarity, it's where you have the result of the radial velocity. So this curve is for one observation, and I had in total 20-ish observations. So this is what we see here on the left panel with all of the observations. And if we take the maximum of each one, we can derive here the radial velocity curve. So it's the one from the red giant. But if you take a closer look, we can see here on the left panel that we have a little bump here and there, like antiphase from the bigger peak. And it's actually the signature and the proof of the companion. So even if its presence is way smaller than the red giant, we can see it. So this is why the system is called a double-lined, because we see the line of both stars. So this is the typical helix form of a red giant, where we see the two components. And in order to get the radial velocity, the value, we performed the Gaussian and Lorentzian fit. We didn't care that much about the precision, or only using one of them, because we only wanted the peak, the maximum. So this is the first conclusion that I have about this part. We have a double-line system, we have the proof of it. The orbit is well covered as well, we can see the maximum, etc. And now, with this and the light curve, we will compute the dynamical mass, so one of the two main objectives. So basically the dynamical mass here, where I talked about the Newton's law, Kepler's laws, we need some quantities. The k is related to the amplitude of the radial velocity. Then we need the eccentricity and the inclination, because the period, we will assume that it's the correct one. And in order to modelize the system, I used the radial velocity data and only the test data, because we cannot use the Gaia data, it's too sparse and too small. And this is the result of the modeling. So I used the Phoebe software, so which stands for physics of eclipsing binaries, so very specific. And here are the intermediate results. So the inclination, so the 90 degrees stands for edge on, the 0 will be face on, so it's okay. Then the mass ratio, so the ratio of the mass of the two stars is 1.06, so they are close in terms of mass. Then the eccentricity is quite low, and another time the period. And the first result is the dynamical mass of each one. So the red giant's 1.46 and the companion is 1.37. So now we have one of the two parts of the work done. Let's move on to the second one, so astroseismology. Basically we took the test light curve, we transformed it into the frequency domain in order to get the power spectral density. And since we studied the red giant as a solar-like oscillator, we could use very famous equations in astroseismology that are scaling relations. So it's the link between measurable seismic variables and fundamental parameters of a star. So basically here on the equation we have the nu max, which is related to the gravity, and the delta nu, so the large separation of frequencies, which is related to the sound speed in the star, within the star. So with this data and the effective temperature that was given by Gaia, we have the second result, which is 1.3 solar masses. So now basically the work is done. So let's compare them and see how it goes into the sample that we said before. So we have here the results. There is a delta on mass of 11%, so it's not negligible. And I added this new target to the sample, so we can see two things. The first one is that it's not on a y equals x axis, but it doesn't follow the tendency of the other ones. So this is why we talked about some axis of improvement that could help determining more accurately both masses, because there are uncertainties in the two definitions of the masses. So we could use spectral disentangling to get the individual temperatures. So it means basically that in the spectra that you have, you will try to separate the spectra of the two stars. And it will give you, among other things, the temperature. Because I took the one from Gaia, like the literature one. I didn't verify anything. Then we could use these parameters to inject them into the Phoebe model. And also modeling the errors, because it was the third part of the Phoebe programming. It was computing the errors, but I didn't do it because it was very time consuming. It was using Monte Carlo methods and everything, so it was beyond the scope of the project. And also we could perform a CCF ourselves instead of taking the template that was given by LCO, because the template given by LCO was calibrated for single stars and not binary stars. So now what's the future of this target? Fortunately, this target is very interesting because it's the first and only known to date star like this, so eclipsing, double line, and oscillating a binary system. And it will be on the Plato field. So this is the main news. So Plato is a mission that will be launched by the end of the year, fortunately. And then I also participated on a paper as a co-author in order to explore how to have a greater and bigger sample, because with the 15 ones that we saw before, we cannot do that much of a science, and we can have many objectives, many results. Sorry. So thank you for listening. Tell me if you have any question. And here we have the poster related to this talk, and also the paper. Thank you.
Thank you, Ines. Thank you for sharing your research. Are there any questions for Ines? No. Thank you again. Thank you.
Thank you.
Huh?
Might be a stupid question, but we know that the Plato mission is dedicated to the study of oscillating stars, right?
Mm-hmm.
And I still don't understand how the study of oscillating stars using astroseismology can help us characterize with a very good precision the other stars, stable stars that are in the mean sequence.
The other stars, you said?
Stars that are not very active, that are not pulsating or not oscillating stars.
Yeah.
Can you explain?
Yeah. So astroseismology is like quite new on the stellar physics domain, and the thing that limits its influence for the moment is mostly instrumentation. We have like our two best soldiers are Kepler and TESS as well, And with the upcoming plateau, we will certainly discover other stars that are pulsating. But because if you don't have the good instrumentation, you can look at a star and say, okay, this one is not vibrating. But actually, with a bigger telescope and a better, like another mission, like plateau, you will discover that in fact this one is oscillating, but you didn't see it before. So now, in astrosmology, you observe the stars that are easy to study with the oscillation. For example, the red giants, in order to get the age of the stars. Then we have Cepheids or Lyrae, for example, Delta Scuti stars that are useful for determining the distances in the universe. So yeah, I wouldn't say that every star is pulsating, because there are, with the convection and radiative zones, there are many mechanisms that can create oscillations. But I'd say that it's a domain that is still increasing, and with the instrumentation, mostly it will progress a lot on the upcoming years.
Are there another question? It's okay. Thank you. Thank you, ENS. For our final presentation for this morning session, I would like to invite Yassine Harrati to present the moving satellite stars for clearer skies with intelligence artificial, with AI.
Hello everyone, I'm Yassine, data and AI developer, and today I will present in removing satellite trails with AI, our personal solution. So I want to talk to you about a problem that's quite getting worse for every astrophotographer in the world, and every survey telescope on Earth, is the satellite trails. So let's start with why this matters. So mega constellations like Starlink, OneWeb are growing fast. Projections put as above 100,000 low Earth orbit satellites by the early 2030. Each one is a spectral reflector, especially bright at dawn and dusk, exactly when many deep sky exposure are taken. So, how has this been handled traditionally? Sigma clipping. You take a large stack of co-aligned exposure, estimate to per pixel mean or median, and reject outliers beyond some threshold in sigma. It works, but it needs many exposures, it fails on short integrations, and it's computationally heavy. It's simply not built for real-time or signal frame use. So our proposed approach flips that. Instead of landing on frame statistics across a deep stack, we train a model to learn trajectory and background directly. It can do instant intelligence pixels replacement from as few as 2 exposures. No deep stack required, and inference runs in a fraction of a second, which makes it viable for near real-time observatory use. Here is the institution using a small toy example. Say at frame 100 a satellite trail crosses a thin strip of pixels moving across the sensor. The system does three things. It takes it track the trail's position frame first by frame. It marks exactly which pixels are covered in each frame, and it measures how far the trail shifts from one frame to the next. Once we know all of that, reconstruction is conceptually simple. Every blocked pixel is copied from the same spot in a clean early frame. For example, frame number 50 in this example. Before the trail ever crossed it, track where the trail is, mark that what is covered, swap a clean pixel from another frame. In practice, that's become a three-step pipeline. First, segmentation. ULO or UNET detector localizes the linear satellite future and produces a precise per frame. Occlusion masks second temporal patch retrieval. The pipeline match spatial coordinates across the frame history to retrieve the corresponding clean background patch. And third one is flow guided Poisson blending. The gradient domain blending merges the retrieved patch seamlessly, preventing visible luminous discontinuities as the same. So, where are we today? So we have an MVP launched. It's still private in my repository in GitHub, but soon will be open source to let everybody, if someone want to contribute. So and we are actively validating its on real observatory data. The core detection and the reconstruction pipeline is implemented end to end. It's been validated on multi-observatory archival exposure sets. It's packaged as a standalone desktop MVP for field testing, and we have established a feedback loop with partners' observation teams. On performance, the core algorithm runs is under 500 milliseconds per frame. We are preserving 80% of pixels outside the occlusion mask untouched, and the model needs a minimum of just 3 frames of temporary history to work. So how the system works? Here is the pipeline end to end visually. An image comes in with the satellite trails. Crossing it, the AI detection and segmentation stage finds those trails and produces a mask. Then temporal and pattern frame-to-frame patching draws in contextual data from other frames and paint the mask region. And outcomes as a stored image with the trail gone and the underlying sky intact. First stage input, AI detection and segmentation, restoration and unpointing, output, and this generalizes the image of any size or resolution. So as you can see here, we have 3 frames: first frame, second frame, and third frame. In the second frame, we have the satellite trails. So we inspired from the first one, so past previous frame and the next frame, to detect in the second frame the position of the trail. Then we get the same image from the first one and third one to merge the image and refill the image that have the satellite frame. So how does performance scale with temporal history? With a single frame, reconstruction error sits around 9 to 10% as we give the model more frames of context. Error drops sharply down to roughly 2% by 10 frames. But notice the shape of the curve. Most of the gain happens in the first 5 or 6 frames and return diminish after that. So in practice, we don't need a huge stack. Just a handful of frames get us most of the benefits. So this is from our solution. So as you can see in the first one, the original image, we have a point that represents a satellite, and in the fixed image we have nothing. So we refill the background we refill the satellite by the background of the previous image. So I won't read throughout every reference, but our work builds on the IAU Center for the Protection of the Dark and Quiet Sky. Tyson and Ali 2020 paper on LEO satellite brightness effect for Robin and LSST. Deep flow guided video and printing person image editing and recent 2025 work on deep learning detection of satellite trails in multi-band image. Full citation are on the slide and in the paper. So thank you so much for your attending, and I will be happy to hear your questions. Thank you so much.
Thank you, Yassine. Are there any questions for?
Maybe it's because I don't really know the subject, but what do you do with shooting stars? Because they can maybe seem like satellites.
Yeah.
So do you remove is it an objective to remove it with the same technique, or do you intend to keep them on the frames?
Can you please reply?
Yeah, do you intend to remove also the shooting stars with this type of AI ideas, or do you want to keep them in the frames?
So no, in the the output. In the output, we remove the satellite trails or the satellite. If it depends if it's point or trails, we remove it and we refill it by real data. How we can get it real? Like we we take the previous data and the next data after that frame when we have the satellite. So we take the same data and we replace it by in front of the satellite. So in the output, it's like merged two images.
Are there another question?
Hi, I have a question about using AI with science. Is there any risk that the AI affects the image that we are receiving from the observation, or it's not a risk?
Yes, always there is a risk, and also the accuracy, it's not 100%. When we can't, I think in my opinion, also in the future, we can't get 100% in accuracy. So always we have, for example, my MVP right now can sometimes it can't remove the satellite from some frames. Like always there is problems, but the AI can affect the data. Yes, I think yes.
Are there other questions?
First of all, I would like to thank you. My question is, how does your temporal matching handles moving celestial objects like asteroids or variable stars so they aren't mistakenly treated as a static background?
Yes. So in that point, if we have like a zoomed camera or like we observe just one like aster or something. In this case, we are working on it in the future, but now we can work just on the images that have like a lot of stars and not just one aster. So maybe in the future we can work on it to develop that.
Thank you.
So first of all, I would like to say hi and thanks for this good performance. My question is this AI model can be improved so we can use it to other kinds of artificial image like noise and cosmic ray hits? Is it possible?
So for now, my solution is for astrophotographers, not for scientists 100%. But as I said, yes, maybe one day we can work with the astrophysicists to develop like new futures to work also on the data from observatories for research. So right now we just for astrophotography.
Are there another question? Okay. Thank you for your presentation. I have another question. It's for the slide where we have two images. One, it's original, and the second one
This
is
one
fixed.
this
Yeah,
one?
this one.
Yes.
I don't see any differences between the
You can
two.
see it because of the monitor, I think.
Okay. So the fixed one, it's not the.
The fixed one, if
You have
can-
applicated the AI.
I have a
artific-
clean image. I can't project it there,
Yeah.
but you are the. It's your question, so I can. Can you see here? I'm sorry, everybody. You can see here. You have satellite here. So this is the satellite what I around.
Which one?
This one. ده اللي فيه شرط satellite. Satellite.
Okay.
هنا غادي يبان فيه يتحرك هنا. المشكلة ديالك شي اللي نتوما فاهمين.
Thank you. And I have another question if you don't have anyone. My question is, are you trusted by the result given by AI? Are you trusted by the result given by AI or no? For now. When you use it,
For now, I'm not satisfied by that work, but I'm always like believe in AI
to give you something.
Yes, in the future.
Okay, thanks. Are there another questions? We still have 7 minutes. If you have another question before closing this morning session. So thanks, Yasin. Thanks for. So that concludes our morning session. I want to thank all our speakers for their contribution and for keeping us on time. And now we will have a pause for lunch break. Please enjoy your break. Thanks.
وقيلة؟ الو؟ وقيلة ما كاينش وقيلة مخليها ما كاينش. الو السلام عليكم. واش انت في زوم ولا لا؟ قلت لك واش انت في زوم تقدر تدخل تبارطاجي الفيديو ديالك باش نتيستيو دغيا 5 مينوت. باش نتيستيو انا وياك قبل ما تبدا مع الجوج. يلا بغيت. هنايا انت يسير الأذان. السلام عليكم. أحمد. الو. اكتيفي المايك راه كتسمعني. الو. الو.
جميلة مزيان دابا.
وي سافا. دير نشوف تيستي بارطاجي ليكرون. راه ديجا ليكرون بارطاجي، غير هو بارطاجي لا بريزونطاسيون ديالك وديرها فولس.
جميلة.
وي احمد كنسمعك، كنسمع حتى الباك جراوند ديالك.
داكور صافي انا كنسمعك صافي سي بون. انا بس البلاصة نشوف واحد معاك شوية على الصداع.
اوكي.
باش نوصل البلاصة.
سي بون ديرها غير اكرون بلان، لو بلان اكرون. احمد. الو.
الله يكون.
كتسمعني ياك؟ كتسمعني؟ كتسمعني؟
على حسب.
لا قلت لك واش كتسمعني بعدا مزيان؟ كاين ديكالاج.
اييه.
صافي غير كبر سميتو ديالك لا بريزونطاسيون ديالك.
اييه.
السلام عليكم سي احمد.
لا صافي باش نحط هذا باش نتكيه. لا
سي احمد كتسمعني؟ الو
نبدو عليك. انايا صافي. الو
كتسمعني سي احمد؟ كتسمعنا؟
السلام عليكم.
السلام عليكم سي احمد، صافا كتسمعنا؟
اهلا الله يبارك فيك. كلشي بخير؟
الحمد لله صافا كلشي مزيان كلشي بخير. نتوما
الله يحفظك. بس
كاين ديكالاج بيناتنا.
بخير. انا راه
احمد لا ممكن تكبر الاكران عافاك باش تكون واجد، دير فول سكرين. الو كاين سوليسيون وات سي احمد؟ الو سميتو باش كنهضر في الميكرو اصو كنهضر معاك ما كتجاوبنيش. دابا تنهضر الميكرو دابا، انا هضر الميكرو دابا وصيفط ليا غير باغ ميساج في واتساب قول لي واش كتسمعني ولا لا.
كنسمعوك ايوب، كنسمعو غير كنظن سيرين ما خداش.
دونك ممكن دير فول سكرين سي حميد؟
سي بون دابا؟ تسمع كون بارطاجي ليكرون ديالي؟ داكور بلاتي.
سي بون سي حميد كتسمعني؟
تسمعك.
اوكي سي بيان.
علي بارطاجي ليكرون ديالك كتبان.
ممكن دير فول سكرين؟ صافي ديجا درتي
الاول
كيفاش ممكن تكليكي على ماسكي سي احمد
نعم
ممكن تكليكي على ماسكي ماسكي اللي طالع عندك في ليكرون الو سي احمد كليكي على ماسكي عافاك سي احمد
وين مراد الو وين مراد
واش كتسمعني ولا لا باش كنهضر في الميكرو
لا ما كنتش وين لا ميكرو لا ميكرو كنسمع قليل الصوت بحال بعيد
دابا
ولكن المهم واش هاني
كيتقطع عندك لا كونيكسيون سي احمد الصوت ما كيوصلناش مزيان
واش نتوما كتسمعوني هذا هو ديك الساعه تنكمل وديك الساعه نقدروا نديروا
جو بونس دابا مزيان
داكور حيت دابا الانترنت هنايا ماشي ستابل
هذا هو المشكل انه كيتقطع عندنا الصوت ديالك ما عندكش لا 4 جي ديالك انت هلو ما عندكش لا 4 جي ديالك
اش قلت مراد
واش ما عندكش لا 4 جي ديالك تبارطاجي زعما غير من عندك
نبارطاجي انا ديجا بارطاجي دابا
وي دابا جو بونس سي بون
دابا فيريفيها الصوت واش مزيان واش كتسمعني مزيان
دابا كنسمعوك مزيان دابا
ايوا صافي سي بون
وي صافي
صافي وليكرون باينه ياك
ليكرون باينه وي غير الا ممكن تكليكي على ماسكي اللي عندك في ليكرون
كيفاش
الا ممكن تكليكي على ماسكي اللي عندك في ليكرون لتحت
نكليكي على ماسكي
وي صافي سي بون سي احمد اخليك ممكن ندير انا هذا سي احمد واش ممكن تحيد لا كاميرا باسكو غير كتاثر على لا كونيكسيون.
Caméra désactivée. ميمورات
ليس احمد غير ما تحيد لاكرون
وتخليك شوف نديروا واحد لا بوسيبيليتي
نحيد لك مصطفى انا حيدتها
تحيد حتى
خلي غير
ونخليو
شوف غندير واحد
دونك انا غندير الميكرو على التليفون عندي
دونك انا
على الواتساب
وي
باش وي
مزيان فكره واخا صافي تلقى حيت الواتساب تسمع بلو رابيد واقيلا ياك
كيتسمع بلو رابيد دونك الا ممكن تاكتيفي الميكرو
بلو رابيد ممكن تاكتيفي الميكرو ديال الفيت
دونك دابا مزيان وي دابا سي بون دونك تنديرو هوت بارلور
هذه فكره زوينه ديرها بهوت بارلور واتساب وصافي
سي بون هكا كيخرج من هنا
الا كنت هكا كتسمعني مزيان
دابا كنسمعوك مزيان دابا سي حمد It's clear for you. It's clear. Do you hear well? واش ممكن دير تبارطاجي ودير فول سكرين سي حمد؟
هاي
اوكي دير
بارطاجي دابا
دير فول سكرين.
هاي
كليك على هذيك
بنت هاي درتها
اوكي خليك معايا. اوكي سو اوكي صافي سي بون. So ladies and gentlemen, I hope that you had an enjoyable lunch and you are feeling refreshed but not sleepy. So we will now resume our scientific program. It's my pleasure to introduce our next keynote speaker, Dr. Ahmed Dassou, who will join us online, as you see. So Dr. Ahmed Dassou is an astrophysicist and researcher affiliated with the Laboratory of Physics, Energies, Environment and their applications at the Faculty of Polydisciplinary Studies in Safi, which belongs to the Cadi Ayyad University in Marrakech. His research focuses on exoplanets, black holes, and cosmology, with expertise spanning astrophysics, theoretical physics, and mathematical physics. Now, his scientific work primarily investigates the thermodynamic properties, critical phenomena, and phase transitions of black holes within modified theories of gravity. His research explores the effects of dark energy, quantences, string clouds, perfect fluid matters on black holes physics, contributing to a deeper understanding of gravitational and cosmology. In addition to the theoretical studies, he has contributed to observational astrophysics through research on test exoplanet discoveries and investigations on Triton's atmosphere using stellar occultations observations. Dr. Ahmed Dassou has authored and co-authored numerous peer-reviewed publications in leading international journals, including the International Journal of Theoretical Physics, Physica and Mathematical Physics, and the monthly notice of Royal Astronomical Society, ENS. Now, his research advances the fields of theoretical astrophysics, black hole physics, and modern cosmology, while fostering interdisciplinary collaborations between theoretical and observational astronomy. So, Dr. Ahmed, the speech is yours now.
So, okay, you hear me? Vous m'entendez bien?
Yes, it's clear.
Okay, thank you, Professor Murad, for this presentation. So I am happy to be here with you today for this plenary talks. I will present one of the planetary science theme we are developing at the Oakhamden Observatory. Is the observing impacts on the lunar surface from Earth using small telescope equipped with a fast and sensitive camera. And it is a deceptively simple method, yet it opened a fascinating window onto the current bombardment rate in the Earth-Moon system and its implication for lunar seismology. So, let me begin with a simple historical question. Can we really see from the Earth's surface a flash of light caused by an impact on the Moon? So, for a long time, the answer was not really, but about 25 years ago, that changes. This has changed, and the detection of lunar impact flash using ground-based telescope became really feasible in the early 2000s, and this thanks to the pioneer work by Rubio and by Ortiz from Spain, by Yanagisawa from Japan and others. And suddenly we had a new window on the inner solar system. So now, why does this matter? So every flash you saw on the night side of the Moon is the death of a small meteorite, typically a kilogram-sized piece of cometary or asteroidal debris, and it gives us two precious pieces of information. First, the exact time, so we can measure the exact time of impact, and the second is the location of the lunar surface, on the lunar surface. So multiply that by hundreds of events, and we start to build a real-time map of the meteorite flux in the Earth-Moon system. This is not just astronomy, so we can say that it's also geology, it's seismology, and it's a tool to understand the current bombardment rate. So today I'm going to present what we made in Morocco to join that global effort. I'll describe how we set up the first lunar flash monitoring station in Africa, and the two impact flash we captured, and what our observation imply for the future of lunar seismology. So let's go back to basic first. So what actually happens when a meteorite strikes the Moon?
Ahmed, désolé.
A meteorite.
Je pense كنا كنظنوا انه ما كيدوزوش لي سلايد but it's okay, so you can go on.
لا chaque slide fait beaucoup de choses à dire.
Okay, it's okay.
C'est bon?
C'est bon.
C'est bon. Merci. So now when a meteorite come in, it can be AC like a comet fragment, and rocky or even metallic. Its speed can be anything from under 10 kilometers per second, and that's typically for asteroid debris. And all the way up to more than 70 kilometers per second, the top speed of a Leonid stream meteorite, and at this velocity, the kinetic energy is enormous. And for example, if we take a 100-gram object traveling at 20 kilometers per second, carries the energy of about 5 kilograms of TNT. So now, here's the K, when a fraction of that kinetic energy, typically less than 1%, is covered into light. And the flash itself, it's extremely short. And for the small impact we're talking about, the whole luminous phase less than a tenth a second. And sometimes barely 0.02 seconds. And that's shorter than the blink of a human eyes. So you need both sensitivity and speed. But the beautiful news is that you don't need a space telescope, for example, a Hubble Space Telescope, but just a mid-sized telescope, something between 20 and 40 centimeters, equipped with a focal reducer to give you a fast field of view and a relatively inexpensive and high sensitivity video camera is entirely sufficient. So you essentially turn the moon's dark side into a giant impact detector, and that's exactly what we did. So now the question, why go to all this trouble? So for me, the stronger motivations comes the lunar geophysics. So we are returning to the moon with seismometers. Think of the Perseid seismic suite, FSS, and the Artemis Area Geophysical Network. So when those instruments are operating, meteorite impact will be one of their main natural seismic source. So if we take, for example, Apollo mission, so for the Apollo seismic catalog, already showed that significant fractions of recorded moonquets are impact generated. But the problem with Apollo data was we really know exactly when and where an impact has occurred, and which made it difficult to study the lunar interior using seismic wave. And now with the simultaneous optical and seismic observations, we can do something truly powerful. So we get an independent ground truth measurement of the impact time from the flash, and we get an accurate location on the surface. So now imagine you're a seismologist, for example, you're a seismologist, and you suddenly know the exact origin time and the exact position of your seismic source, and that converts an meteorite hit into a calibrated seismic shot. So from that you can prove the crust, maybe even the mantle with much higher precisions. And there's more impact flash also feed into lunar atmosphere, and that's study. A mission like, for example, like LEDDE benefit from knowing when and where material was injected. And they help identify a fresh impact crater with a rock before and after imaging. So finally, the optical monitoring is a low-cost, high-impact complement to any lunar surface missions. So about monitoring lunar impact flash from Morocco, so how did Morocco get involved? So we had two sites. The first one was at Atlas Gulf Marrakech, which served as a test stations, a way to gain experience with the hardware, the observing protocol. And the second one is our main observatory, was at Oakhamden in the high Atlas mountain. So let me give you, for example, the coordinate, because the matter. Oakhamden's site is located at latitude 31 degree north, at longitude 7 degree west, at an altitude of 2,700 meters, and in that altitude, that altitude gets us above a lot of the atmospheric turbulence and dust. The second observatory is Atlas Gulf, is lower at about 470 meters near to the Marrakech. So why are these sites interesting for impact flash work? First, for the geographical positions, because we feel a longitude gap in the international network, and to confirm an impact is real and not a cosmic ray hit on the camera chip, you need a simultaneous observations from at least two widely separated telescopes. And in Morocco, with its clear sky and southern latitude, we can observe the moon when the European station may be clouded out, or when the moon is low for them. And the second thing is the astronomical seeing at Oakhamden. The astronomical thing at Camden can be very good and regularly around 1 second, which helps help with the precise localization of the flash on the lunar disk. And third, the steady atmospheric conditions in the desert often mean we can run long. And monitoring run, so which is exactly what you need for catching a rare and subsequent event. So now about the observation period of lunar impact flash. As you know, you cannot observe impact flash on any night you like. The image on this slide show why we always and we always look at the dark illuminated. The dark is an illuminated part of the moon, and the earth chain region of the pure night side. And when a meteorite hitting the brightly lit crescent of or gibbous parts simply get drowned in glare. So our observing window is strongly tied to the lunar phase. We typically start a few days after new moon, and when a thin crescent is visible and a large dark area face us, we continue until we continue our observation until first quarter. So then the illuminated fractions become too large, and the contrast drop, and we have contrast drop. And in this case, we have to stop. The same happens in reverse. We can observe again from less culture until a couple of days before new moon. And in practice, the sweet spot is when the moon is between about 10 and 50% illuminated, and that gives us roughly 6 to 10 nights per lunations. And around full moon, the whole disk is lit, and there is no and this time there is no dark area, so observation are simply impossible. So I like to show this because it reminds us that patience is a key part of this science, and you spend many nights waiting. So you spend many nights waiting, and then you capture one flash at least at 0.08 seconds. So now let's open the dome, and I will explain to you the instrument that we use to monitoring lunar impact flash. So what did we actually use? Our main telescopes were commercial Schmidt-Cassegrain, a Celestron 8 and a Celestron 14. So the C8 is an 8-inch, C14 is of course a 14-inch, and both are compact, as you know, robust and easy to automate. So we mounted a focal reducer on each. For example, for the C14 we used a 0.6 reducers, and on the C8 we could go down to 0.33 reducers. Of course, this is critical, and it's shortening the effective focal length and give us a faster focal ratio, around f divided by 3 to f divided by 4, and within the field of view, and we were imagine a field roughly 20 by 15 arc minute, enough to cover a good chunk of the lunar night side. So about the camera that we use, it was a Watek and a teeny but extremely sensitive analog video camera. This camera operates at 25 frames per second, and its high gain lets us pick up magnitude 9 or 10 flash on the dark mode. So the analog signal was digitized by a frame grabber, but the key piece of hardware was the GPS time inserter, and it stamps each video feed with the universal time to milliseconds per second. without that, our flash timing would be useless for seismology. So on the software, about the software, we use the virtual dump to compare the video stream into AVI file, which we could later scan frame by frame for brief brightening. Altogether, the whole system cost a few thousand euros, so a fraction of what would spend on a typical professional astronomical camera, and it's an elegant, low-budget setup, and it works. So now, for the health of the story, our first two flash, so both captured from the Atlas Gulf Marrakech Observatory. The first one occurred on February 6 in 2013, and the second followed on April 14 in the same year. So you can see the title page of our 2015 paper on the screen, and I still remember the thread of watching those brief speaks appear on the video. So the table that you show on this slide summarize their measured characteristic. Visually, the flash reached magnitude of 9 and 7 respectively. The first flash have a magnitude of 9.4 and the second is 7.7. Even the front one is well within the reach of our modest optic camera, based on this luminosity and the typical impact, and we derived the meteorite mass of 0.3 and 1.8 kilogram. And if we assume a density of 1,500 kilometers per cubic meter, and typical for porous cometary material, and thus can give mass of this two flash of the impactors, and those mass translate into objects of about 7 to 8 centimeters across the event, and 14 to 15 centimeters for the second. In other words, the first was roughly the size of a tennis ball, and the second the size of a small melon. So, and what did this small projectile do to the lunar surface? So we estimated the producer crater of about 2.6 meter and 4.4 meter in diameter. So from an optical flash lasting a fraction of a second, we can deduce the size of the impactors and the scale it left behind. So a beautiful piece of planetary forensic. So now, let me be completely transparent about an important point. So these two events were not simultaneously confirmed by a second telescope in the network. Therefore, strictly speaking, we cannot exclude the possibility of a non-lunar origin, such as a cosmic ray hit on the detector. However, their light curves showed the aspects in this by these figures. The way they rise and fall, and their color and formation, and also their occurrence on the dark lunar side are all entirely consistent with compact flash. For this reason, we discuss them as a highly probable impact event, while they need for multi-station validation in future company of observations. So now, one innovation we are particularly proud of is the localization method. So to determine where on the moon this flash occurred, we didn't need the precise knowledge of the telescope pointing or lunar librations. Instead, we used features of the lunar surface illuminated by RG. So the fine glow of sunlight reflected from the Earth onto the dark moon And by matching the flash position relative to those Earth-like craters and the Maria, we could pinpoint the selenographic coordinates directly from the video frame. So the results are about 8° south and 60° east for the first flash, and 30° north and 9° west for the second. And this position plays the impact in the lunar highland far from the Maria. And you can see that the method is elegant because it works without any external geometric input, and it opens the door to rapid flash localization for seismic source identifications. So that side, for high precision seismology, we will need even better localization accurate, perhaps combining earthshine based mapping with the simultaneous observation from multiple sites. So these two flashes marked the very first lunar impact event recorded from the African continent. They showed that the observatory in Morocco can contribute to a global monitoring network. And they give us a first test of the scientific potential. So from a fleeting point of light to the mass of a meteorite and the size of a fresh crater, and this all captured with a commercial telescope, a small telescope, and a sensitive video camera. So, now of course, we weren't blind to the limitations. So the main one is that a single telescope can only report a candidate flash, and without a simultaneous detection from another distant observatory, you cannot be certain the event is from the moon surface or not. So a robust network is not a luxury, it's a necessity, and we learned that to increase the scientific return, so we needed more partner stations, ideally spaced across longitude. So a second shortcoming during all the company of our observation is was tracking. So as you know, the moon is drift, and if your telescope doesn't take perfectly, the light of a flash can smear across several pixels, and this can reducing the signal to noise rate. And we were using manual or semi-automatic grading, and adding a good autoguided system located on a layer feature, and would keep the image rock steady and improve our photometric quality for future events. One important thing is we also noted that our visible light observation only gives us a tiny window into the impact physics, because the flash is in the optical is extremely brief and represents just the initial radiative peak. So to understand the full energy deposition, the thermal glow of the hot ejecta, for instance, and we need to expand in the infrared. So that brings me to the future. So as you saw in this picture, our immediate goal is to expand the network, and we are actively looking for additional collaboration. We share additional collaboration in Africa, in Europe, in Asia, and maybe in South of America. And why we need more station? Because more station mean more simultaneous detections, and mean also higher confidence and better orbital quality impact locations. So the second thing is a very promising avenue is to observe simultaneously in the near infrared. Why observing in infrared? infrared, because in the infrared, sometimes several tenths of a second, even a full second, because you observe the cooling of the hot vapor and the mean droplet. And this not only increases your detection efficacy, but it also gives your physical information about the impact process. So finally, all of these feeds directly into the coming area of lunar seismology. When the next generation of seismometer is deployed on the moon, so I dream of having an optical network that can trigger alerts in real time. For example, we can telling the seismologist that an impact just occurred at this coordinate at this exact time and go its seismic signal. So that is the bridge we are building, and I can say that it all started with these two tiny flashes in the Moroccan sky. So thank you very much. I'd be happy to take your questions.
Thank you, Professor Ahmed, for your nice, well-organized and pedagogical presentations. We pass to do questions if anyone has questions here. Okay. It's okay.
Bonjour, Professor Ahmed, معك عبد المجيد بن حيدة. Thank you very much for your fascinating presentation. I have just one question about the evolution for equipment to observe lunar flash. Yeah, and my question is, what do you need? I think that you have talked about infrared camera. Yeah, to continue this program in Ukaimdan Observatory, and you know that we have a new program with the Saudi Arabia. So yeah, they want to observe lunar talk. So what do you think that can we in this program we continue the program for flash lunar in Morocco? Thank you.
Yes, of course. As I presented in the last slide, we need to observe in the infrared camera, and I remember that we started to observe in infrared, but it's not the good camera. I remember that is the camera for imaging, for biology, or something like that, but it's not for astronomy. For detecting the flash. So, today I know that we have new technology of infrared camera that can use for impact flash, to observe the impact flash, and this is very important to observe impact flash because we can detect the flash long durations, and we can. We can study the evolution of the Doppler on the emitted after the flash, and it's possible from Ukaimdan. It is possible because we have a telescope, a C14 telescope, or maybe a C8 telescope, and if we can buy this camera, big infrared camera, we can detect more flash than we detected in 2015. So I think it's very important to continue to observe the impact flash in the infrared wavelength, and one thing is important is to observe in networks. We need to collaborations to confirm the detections from because detector one flash for one observatory is not sufficient to confirm the detections. It's just a candidate. But if we have 2 or 3 telescopes that observe in the same time the same event, we can confirm or not the event, and we can better characterize the flash. We can better detect the position of the crater. We can better estimate the diameter of the crater. We can the kinetic energy of the impactor, the velocity and other characteristics. All these characteristics can better we can better have this characteristic with a precise, with good precision if we have a network that observe the impact flash.
Thank you, Professor Ahmed. Just a question on the price of this of the infrared camera. How much is the infrared camera? It's a question that is transferred to you.
Okay.
If you have any information on the price of the needed camera, the infrared camera.
Price.
Yeah.
I think in Morocco, 20 millions 200,000 dirhams. In euro is
2,000 euros.
2,000 euros, yes.
Yes, 2,000.
Yes, from 2,000 euros. Yes, from 2,000 euros, yes.
So I think now, as you know, we have lots of instrumentations for professional and also for amateurs at Oakhamden Observatory, and it's the good time to continue to build on what it has already been done with you, of course, and the other researchers. It's a good opportunity to continue in this on this project of studying the lunar flashes. So
yeah. Yes, exactly. It's very important to continue to observe the flash impact. And one more thing is there is no flash up to now. There is no flash detected in infrared. If we can observe a flash with the infrared camera,
do you mean from
the first
observatory, from
time.
Morocco, or from all the world in the infrared?
No, all the world. There is no observatory in the world observe the flash in the infrared.
Oh, thanks. It's I think it will be
If we can, if we can detect the first flash in infrared, that is the first time in the world. It will be the first time. Yes. All the flashes detected up to now is detected in optical camera with using the optical camera.
In the optical range.
Yes, exactly. In optical waves.
Okay. There is another question.
So you talked about a lot about how to detect moon flashes, but is there any currently known usage for the data you collected, or is just data for the moment?
Please, I don't. Can you repeat your question?
So you talked about moon flashes. And mostly how to detect them, like and to gather data from what causes the flash and this kind of things. Is there any known usage of the data you collected for the moment? Like, I don't know, studying, just flying rocks in space, all these kind of things, or not really for the moment?
No, yes, of course. There is a lot of observatory. For example, in Spain, there is an astronomical called Ortiz, is the first one detects the first flash in 2000, and from this year we have another teams that observe in Japan, in the USA also. USA, they have a lot of flashes that observed from other observatory, but just in optical waves, using just an optical camera. Is this your question?
Yeah.
Other questions?
Thank you, Ahmed, for your presentation, for this inspiring talk. And I have two questions, please. For the first one, I want to know why are they important for understanding and studying the moon's environment? And the second one, it's about how do you distinguish between the Lion's impact flashers and the solar satellite crossing or instrument waves?
Okay, thank you for your question. So about the important to observe the flash impact or the environment of moon. This is important for the future space mission. So for the future space mission from NASA or ESA, it is important to detect or to know information about the flux of the meteorite hitting the moon or hitting the system moon Earth. It's very important, and this can help this mission to know, for example, the better place that can take or that can install the instrument without danger, without to have a problem in the future. And an important thing is to detect the seismic source, because an impact flash, when a meteorite hits in the moon, the surface of the moon, we can consider this as an seismic source. And this is very important to study the geology of the moon. So if we can detect the seismic source, we can, by installing a seismometer, we can have an idea of the interior geology of the moon. We can have the more information about the geology of the moon, the interior also of the moon. That's I think your first question. And the second question is, can you please repeat your second question?
The second question is about how do you distinguish the Lion's impact flashers from satellite crosses or instrument waves? Yeah.
Okay, exactly.
How do you
it's a good question.
between two phenomena?
Yes, it's a good question. When we detect a flash from camera, we divided the video frame by frame to have how many image the flash appear. And if we divided the video, we can show the variation of the luminosity of the flash. For example, we have a peak of intensity and you have a minimum around this peak, minimum intensity. But if we have a cosmic ray, we have a brightness constant. We have a luminosity of the ray cosmic is constant, but the luminosity of a flash is varied. It changes if we go frame by frame.
Okay.
So this is the difference between This is the difference between the luminosity of impact flash and the noises like cosmic ray. The cosmic ray luminosity is constant. We have a constant brightness in all image. But when a flash appears, we have the brightness is changed, and we have a peak of brightness, very, very clear.
Other questions? May I have a question, Professor Ahmed, please?
Yeah.
Is there any synergy between the ground-based observations of the lunar flashes and any space mission sent to the moon? For example, you said that flashes can be exploited for seismic studies of the moon to constrain the interior composition of the moon.
Yes, exactly.
Is there, for example, any mission dedicated to installing, for example, sensors in different longitudes or latitudes on the moon that can be used to detect the seismic wave, the seismological, or the seismic waves when there is any flash or any crater?
Yes. In the past, we have the Apollo missions. The Apollo missions is an instrument, seismometers, to detect the seismic source. But the problem with the seismic source, we cannot detect the time exactly of the impact. We have this. We need this information. The seismometer cannot detect perfectly or exactly the time and the position exact.
With
so
operation, for example, is there any, for example, they can, for example, do many, at least 3 sensors at different places, so they can constrain the exact location of the flash on the moon, and that can be used in synergy with ground-based observations from ground.
Yes, it's possible. Yes, it's possible. I think in the future mission, Artemis maybe future mission can install a new generation of seismometer, and this information captured by this instrument with complementarity with the detection from the Earth, we can give a precise information about the impact. More information about the impact and more information about the seismic source, and to get precise information about the geological of the moon, geology of the moon.
Any other question? So no other question. Thank you a lot, Mr. or Professor Ahmed. So we know you very well, and we are really happy to collaborate with you, of course, because you have interdisciplinary. You work on cosmology, black holes, moons. You are versatile. Thanks a lot. Thanks again.
Thank you for you also for the organization, and thank you for all the participants. Thank you for.
Thank you. Bye. So now we can move to the other talk, which will be given by Thomas Floss-Panu on the physical study of the sun.
Thank you. Okay, so good afternoon, everyone. Just for the time, so yes, I'm going to present my work that I've done in a preparatory class for engineering school called ICAY. It was about a physical study of the sun involving statistical physics and observation in goal to determine the sun nature. So, first of all, okay, so yes, the idea behind this work was to determine the sun nature with only basic tools which we can have in high school and in class papa, and so to have a scientific process in validating or invalidating the result we had with the theory thanks to the experience. Okay, I got it. So first of all, just an historical point on this field. So in the beginning of the 17th century, an optician, Holland optician Antley Bosche, invited the luneta, and then Galileo Galilei used this luneta to discover many different astronomical objects, such as the Jupiter satellites, and then he used it also to study the sun, and he discovered the presence of sunspot at the surface of the sun. And this is a drawing done by Galileo at that time. And another scientist, which I found particularly interesting in this work, was Johannes Fabricius, who discovered at that time that, in fact, sunspots are motionless on the surface of the sun. So by studying movements of sunspot, we are currently studying the movement of the sun at this latitude. And 200 years after this, Richard Carrington, mentioned before by Professor Aziza Boumir, discovered the rotational, the differential rotation of the sun. So the thing that the sun doesn't rotate at the same speed in function of the latitude. So here is also a drawing of Carrington done in the middle of the 19th century. Just about the theoretical approach I wanted to have. So the goal was to develop some mathematical equations which will help me to find the physical nature of the sun based on only measurable parameters. Because if you have equation that you cannot do anything with, it's not interesting at all. So the point was to have enough theory to use it, then to have result on the sun nature. And so to have answer on this question that if the sun is solid or fluid, or even, as we will see, a ionized plasma. Just to begin, I will use in this demonstration the virial theorem, so linking the kinetic energy and the potential energy. But the point was how to interpret these energies. So first of all, we interpret the potential energy of the sun as the energy needed to form the sun through layer of accretion. And we can demonstrate that this potential energy follows this formula involving the sun mass, gravitational constant, and the radius of the sun at the equator. So those are parameters that we can measure, so that's interesting. And then we consider the hydrogen atoms which form the sun. So they have 5 liberty degrees, and if we write n for the number of hydrogen atoms which compose the sun, we can have, thanks to the equipartition energy theorem, the value of the kinetic energy involving the Boltzmann constant and the average temperature of the sun, which we want to find. So if we do the approximation that the sun is only composed of hydrogen atoms, which is not really incredible, because it's not enormous because we know, thanks to spectroscopy, that the sun is composed by 74% of hydrogen atoms, so it's fine. And we have so this formula which gives us the average temperature of the sun. If we use the third Kepler law to determine the mass of the sun, we can find that the average temperature of the sun is about 10 to the 6 Kelvin, which is accurate with the literature, the scientific literature we can find. Then the idea was to use new tools, and in particular, so statistical tools. So let's imagine that the sun is a cloud composed of particles at the beginning, so n hydrogen atoms, called N0 at the beginning, and some free electrons, which will impact the ionization of this cloud. So we have several processes which will happen in our cloud. So first of all, we have ionization by electron collision. So an atom of hydrogen will receive an electron and be separated in a proton and then two other electrons. And we have two other phenomena, which are so quantum phenomena with absorption and liberation of photons, and they are quantum phenomena, and we will much more focus on the first one, which is the main process in this evolution. And so we have, thanks to the negligible of the electron at the initiate at the beginning, we'll have so the evolution of the number of hydrogen atoms in our cloud following by this rule. To determine how we'll evolve the hydrogen atoms, I wanted to use the Bohr model for hydrogen atoms. So Niels Bohr, a Danish physicist, postulated some constraints on the kinetic moments which the electron can take. So here we have the Planck radiate constant, and G is an integer, and so he postulated that the electron could only take those values of kinetic moment, and if we do some calculus thanks to maybe second law of Newton, we can find that the radius and the energy which can take the electrons is also quantified, and here we have a schema which represent the different values that can take the electron, the different energy values, involving also other constant, has the Planck constant. And then for the statistical part, I wanted to use the Boltzmann statistical law for an electron to be in a certain level of energy. So this formula, we can demonstrate it for the example on the case of the isotherm atmosphere, with considering an infinitesimal cylinder of air, and so he will, thanks to the different equation, has the fundamental thermodynamical equation and also the perfect gas law. We have differential equations with solutions in exponential, and that's why we have here probability depending on an exponential also. And in our cloud, we consider that hydrogen atoms are ionized if the electron is in high level, so low level of energy if we look at this formula. And so then we have the probability for an atom to be ionized. So the event that an atom is ionized is the event that this level of energy of the electron is more than 1, so 2 or else. And so the probability 1 minus the probability of being in the fundamental level. And so we can find by calculus the value taken by Z in the constant, the multiplication constant. And so we find the probability of ionization for an hydrogen atom. And then to this, and considering the Pauli exclusion principle, we have this equation, so the equation, psi equation, which link so our different parameters with the relative ionization particular density. So which will give us the state of our cloud, so how much atoms have been ionized in this process with collision with electrons. So about the numeric result we can get for the de Broglie for the de Broglie wavelengths we have so about 10 to the minus 11 meters. We know that the fundamental energy state for an electron is about minus 30.6 volt electrons. If we took a density of 10 to the 32 hydrogen atoms at the origin per cube meter, we then have so this value of ionization for the sun 0.62, so that the sun is ionized at a level of 62%. So in that case, with so this formula, thanks to the psi equations, we can determine that the sun is a ionized plasma. Then we will try to demonstrate and validate or invalidate this experimentally. So I wanted to use the Carrington method. So Carrington at that time only had image through telescopes and only some element of spectroscopy, but we will here use rather the mention of sunspot at the sun surface. So if we can, if we take a sunspot at a date t and then his motion dt time then, we can have so the distance which has been taken by the sunspot and so its velocity at this latitude. Due to our place on Earth or in space, we have a certain geometry. If we look here in the front sun schema, the sun is not a cylinder, so we have different radius depending on the latitude, which we can get simply with a Pythagorean theorem. And also the sun, if we look here of a situation above rather than in front, with above situation, so the sun is in 3 dimensions and not in 2 dimensions, while we are observing only images. And so what we can measure is the two distance d1 and d2, and the real distance which is taken by the sunspot is so the big distance d, which we can get with this formula involving axis function. And so the idea of this method is to see if the angular velocity is not a constant, has a latitude function, then the sun cannot be a solid and is necessarily a fluid. About the data I used in my process, I chose to use SO satellite database. What's really interesting with SO is that he's placed on the L1 Lagrangian point. So we have not the problem of Earth rotation on itself, and so we have images on the sun every 30 minutes, which is really interesting to follow a sunspot. And so we have now synodic velocities. In fact, the velocity in reference of the sun for return to the same part of the surface of the Earth, in that case on the surface of SO satellite. And so I took photos from SO satellite and then I put it on GeoGebra tools that I've made, and so I have the position of the sunspot. And by having 2 images per sunspot, I have the average velocity, angular velocity, taken by this sunspot. And so that's the curve I obtained with this method. So we have in blue the theoretical curve, which is following this formula, which we can find in the literature, with lambda as a latitude. Here we have so the latitude and the angular velocity in function of the latitude. We choose these unities to be representative and to be easy imaging by people. And so here we are, a study done on 50 sunspots. We see that there is a maximum of angular velocity on the equator of the sun, rather than on the high latitude in positive case, that we have less angular velocity in that case, and that the error bars are really disjoined between angular velocity at the equator and those at the high latitude. So even if my fit curve is not perfectly on the theoretical curve, we have sense between the measurements, and that error bars are disjoint, and so that the angular velocity cannot be the same at the equator and at the high latitude, and so that the angular velocity is not a constant of the latitude, and so that the sun is a fluid. So in conclusion, we have been able to develop a theoretical method to determine the sun nature thanks to statistical physics, and then we validated experimentally through observation. I just wanted to thank some people who helped me in this process. So Guillaume Montagny and Véronique Chojnaki, who were my physics and astronomy teachers in high school with whom I began this work. Then Delphine Arcizé, my physics teacher in class repas, who helped me with this paper, and so Nadège Meunier, who helped me a lot for the demonstration and gave me many papers and ideas to follow the theoretical part. Thank you for your attention, and I hope you have questions.
Thank you a lot, Thomas. So, if you have any questions, please.
Thank you.
I wanted to ask, first, thanks for your speech, and then I wanted to know how did you intend to erase kind of the difference between your fit and the theoretical model you thought you wanted, and where this difference could come from?
In fact, so I've done several uncertainties, like you can see here in the error bars. So I've took different ideas coming from the non-linearity of the Axion formula. And so if we take sunspots which are on the very far side of the sun, if they are not in the center, you will have a lot of trouble because of the Axion formula and the non-linearity of this function. And so I tried to use much more sunspots which are in the center of the sun to study their velocity, to have less error, and we can see on the diagram that there is some sunspots which fit clearly much more well than others on the theoretical curves, and that's a reason of evolving in my method, and also what I wanted to do because of the sun mechanisms in the surface. With convection cells, we have a lot of movement on the surface, and plasma movements, and so sunspots are not in the time, have not the same form. They are getting trouble because of other parts of the surface, and so they are modifying their forms, and it's really hard to follow them. So by having less time between the photos, we have less deformation, and so we can keep the right position of the sun for the surface.
Thank you. Any other question?
Hi, thank you for your talk. My question is about the statistics for your fitting part. If we could go to that slide.
Yes. You're talking so about theoretical.
The comparison between the theoretical model and
on this curve.
Here, the first thing is how did you do the fitting? Because you had, I mean, you were trying some mathematical expressions, or how did you do that with a program or?
Yes, in fact, so as I said, I used GeoGebra tool to have the position of the sunspot, and then I put it in a text file, and then I used a Python program to have this curve and to do all the different uncertainty on it by a statistic method, to have A method and a B method on how much my precision is relative with this method, because the image is not perfect, so we have uncertainty about the thing that this pixel is black or this pixel is in the sun, and so we have error on positions which have to be taken. And so yes, I used a Python program to fit by statistics my point with the curve.
Another question is, the error bars were calculated by you or were given by the instrument that you used?
Sorry?
The error bars, the uncertainties, were calculated by you?
Yes, I've done the error bars. I tried by combining the two methods, both statistical, so by doing again and again the measurement on the same sunspot, using I use this by hand for some sunspots, but it was really busy work to do, so I rather use statistical and simulation on Python using I don't know if it's international methods or Monte Carlo method, to have a simulation of how the value depends on my parameter, and then I used also error on my measurement technique to have this idea if my measure are good or not.
Any other question?
Thank you, Thomas, for this presentation. I have one question is for this plot here, this figure. You plot this figure in which phase of solar cycle? It's have you integrated the variation of solar cycle in the solar cycle? Yeah. In which phase you have plotted this? You have calculated the velocity of the sunspot as a function of the latitude. It's a maximum, or it's a minimum phase, or it's the sun. Yeah. And
yes, that's interesting. As Professor Hazis Bounir told us yesterday, there is some oscillation in the number of sunspots we can have on the sun surface following the Schwabe cycle with some maximum and minimums. And so that's a question I asked myself when doing this work, because I had troubles in finding good sunspots to follow, because as I said, they are deforming a lot, so if I don't have any much time to measure them, I couldn't have any correct velocity on it. And so I tried, this data is from, as I said, I began this work 3 years ago, so it was 2024, 2025, and the beginning of 2026. And so it's a good question by taking if the sun is at a maximum of activity or of a low activity, because it could impact the motion of sunspots at the surface. And so this is really interesting, because it has to be taken part, I think, in involving my work in the uncertainty of the data I use. Yes. Thank you for your question.
Thanks a lot.
Is there
I think
any
there is no
question?
other question.
Oh, yes, Baptiste.
I think it's okay. So,
in the middle.
Given that, okay, no other. The last question.
First, thank you for your talk, and for the sun phase, the sun activity phase, do you think it can affect the results by changing the viscosity of the sun or the motion of the upper atmosphere of the sun and changing significantly your results, or is it just in the hour bars?
Yes, as we were saying, there is impact of the sun activity on the surface because of the cell models of convection, with matter coming from the earth of the sun, to the surface. So the plasma is coming from the. In fact, I haven't explained at all what's a sunspot. A sunspot is a locally magnetic field of the sun deformation, and so the plasma on the surface is not anymore fed by the heart of the sun, and so it is impacted by the cell convections of plasma. And so if we have a deformation of the sun activity, we have an impact on the surface on the sunspots, and so they can they can have different velocities because of the difference of activity of the sun. Clearly, I think so.
Bunch of thanks.
Thank you very much.
Thank you. Given that there is that some of the speakers canceled its presentation at the last moment, and based on the request of one of the participants, Asma Randor, are you here? Asma? Donc, based on her request, she will give a presentation right now. Can I talk now? Yes. Micro. هي الاسماء. Oui. Yeah. هو قلت. So it's okay, the speech is yours.
Okay, so hello everyone. I hope you are doing well. My name is Asma Randor. I am a meteorologist in the city of Saroudan in Morocco. So I would like to present to you a research paper that we did through a citizen science program. It is about the double star system. So first, I would like to present to you an organization that help us to participate as amateurs in that kind of papers, which is Pan-Africa or PAX-E Lab. So they do a lot of projects like asteroid hunters, exophotometry, double stars, astrometry, which is the one that I am going to present, the astrophotography, ICE, which is a participation to ask astronauts in the ENS questions and they reply to us. I did participate on it and took a certificate from it. I did participate also in the asteroid hunters from Morocco. So yeah, those are the highlights of projects. So this is our paper. To participate, it is completely free for all all amateurs from African countries, but it should be 3 or more participants. So those are my colleagues and friends in this paper. So first, I want to ask about what is the objective of our paper. The objective is looking for a double star and seeing their previous data and measuring right ascension, separation, and other parameters, and see if there is a new, doing new measurements, and see if this double star is a binary or not. So why we are looking in the space for binary stars? So binary stars are very important in astronomy for studying the evolution, stellar evolution of other stars, and knowing their mass, and understanding more how they evolve. So now I'm going to present some websites that we use for obtaining the data. The first one was the WDS, Washington Double Star Catalog, which is below right now. And US Naval Observatory, we do send to them an email and ask them to give us more information about the target double stars that we choose. Also, there is Celedopi that we use for searching for the double star that we are interested in. And finally, the Gaia data release tree. It is a website of NASA. It gives us parallax and proper motion of the stars. So this is the target double star that we choose using Celedopi. For choosing this particular double star, we like a lot of properties for it. The first one is that the delta magnitude, which is the difference between the magnitude of the primary star and the secondary one, is for magnitudes, because we just use a small telescope of 0.4 meters, and we need a bigger difference, a smaller difference, sorry, to be able to see this, to see them through the telescope. Also, the magnitude of the primary star is bright, 9.7. The separation between the first star and the secondary one is 6.5. So it is interesting one, because in 1932 the separation was 6.5, and in the 2015 it became 7.3. There is a difference, but we want to know, because we want to know is it going to be smaller or be a greater separation in the actual time. So for having the images, we use the Las Cambres Observatory telescope. Especially, we get our images from the Trinity Observatory in Canaria. So we give to the Las Cambres Observatory the parameters that we want. So we want 10 images, and we use all those criteria for getting our images. This is the image of the telescope. So we use also astrometry.net, which is a website which is free. You can use it just for if you have images by your telescopes and you want to have better pixels, you can use it. We use also the AstroImage application to analyze our 10 images. This is just one of the images that we get, and measuring their position angle, the difference between magnitude. Yeah. So those are our measurements. We have all the 10 images and calculated the mean, standard deviation, and the anomaly or the error. And this is the graph represents how the data difference change with time. And this is the last in 2024. This is the last measurements that we get. Next, calculations. There is some calculations that we use. The first one, which is obvious, the parallax formula. And the second one, which is interesting, we use a relation, equation of relative proper motion. And we found out that this relative proper motion is 1, which is less than 2. That means that this double stars is not likely gravitationally bound with the secondary one. So finally, our results for all the data that we get, that this double stars is not unlikely not binary stars. So yeah, thank you.
Thank you, Mrs. Asma, for the presentation. So, do you have any question? So, no question. I think it's okay. So we can go now for a coffee break and a poster session. So you can pose your questions and discuss with the presenters there.
Hello everyone, I'm Ayub. I'm a PhD student in astrophysics at the Cadi Ayyad University. So here I'm presenting my research work on working on the photometric characterization of low Earth orbit satellite from the Camden Observatory. So first of all, as we know, in the recent year, the low Earth orbit satellite has a real concern on astronomical community. For their brightness, they are very bright and visible to the naked eye. Sometimes leave a streak in our images. So for that, we need to understand and assess their impact on the astronomical observation. So we measure we have to measure the visual magnitude of the satellite as it a direct measurement and indication of how strongly this satellite interfere in our observation of optical telescope. So first of all, in our study, we use 3 robotic telescope from the Camden Observatory. Each telescope track satellite using a sidereal mode with a single exposure time. So to make sure that each satellite appear as a trio in the images without expanding in the bore of the frame. To schedule this observation, we use an app to update TD data. This data has contained the element, the parameter element of this satellite that tell us where and when this satellite will be in the sky. Okay. After that, we go after taking our images, we go to data processing. Data processing consists of determining and measuring the visual magnitude of the satellite using photometry and the nearby stars, the reference nearby stars knowing from a catalog like Gaia. So each images has to go through calibration, astrometric calibration, to make sure each images has plot solving and WC calibration. After that, noise reduction, and after we detect this trial in our images using pipeline program in Python. Each trial detected. After that, we use aperture photometry to extract the integral flux of the satellite of this trial, and using the comparison stars detected from Gaia catalog, we extracted the visual magnitude. So in our result here, it shows our measurement, 115 measurement of the star line. It shows that the apparent magnitude is about 6.6 magnitude, and after adjusted to a normalized distance, like for here, 515 kilometers, to show how much the satellite will appear at this reference distance, to make a real comparison of all star line. It shows that the magnitude is 4.6 magnitude. So critically here, our measurement it shows that more than 80% of all the star line measurement is above the EI recommendation. For example, for 100 kilometer, the international community recommended satellite it should be 8 magnitude, but the real measurement show that these star lines are still brighter and below than 7. More than that, this measurement it showed that the brightness of the satellite is not like a star, constant, but it change and have several parameter geometry parameter like altitude, phase angle, and orientation, and also it's depend on several the surface characteristics of the materials that build this starlink are built. More reflected means that this satellite will be more bright. And thank you for your answer.
Thank you, Sir Abdul. So we pass to the other. Do you have any questions? If there are any question, I'm happy to take it. No question? I think it's okay. So thank you. We pass to the other poster, which is for Hisham Sriba. So the speech is yours.
Hello everyone. I'm Hisham Sriba from University Cadi Ayyad. This work presents the particle emission spectrum and thermodynamic of charged at the S black holes in massive gravity. The black holes thermodynamic has been a rich field since Hawking, Burden, Carter, and Page since in 1970 has become a rich research area. The study of black holes shadow gained major momentum after the event Event Horizon Telescope's first image of 87. Our goals are three objectives. The first, investigate the shadow and energy emission rate of the charge at the S black holes in massive gravity. The second, develop a new way based on maximum emission frequency to probe the thermodynamic and phase transition criticality. The third, link the thermodynamic behavior of the black holes to at maximum emission frequency for the both photons and massive bosonic field. In classical thermodynamics, we start with the definition of metric function in 4 dimensions. In massive gravity, usually for at the S black holes, Rn at the S black holes, then we define the other parameters characteristic, ou bien the other parameter thermodynamics, such as the pressure, the entropy, the Hawking temperature, and the Gibbs free energy. In the right, we plot the Hawking temperature as a function as the Reason radius for multi values, the lane rate for the subcritical value with the two rods. That's the signature we use well to identify the first order phase transition. For energy emission rate, the black hole's shadow is the high energy absorption cross section seen by an observer at infinity. It's equal to photon sphere area. This formula led to the classical Wien's law displacement. For massive field, we can derive the anneau or the generalized Wien's law displacement as a function of mass graviton In the right, we are plotted the energy emission rate as the function of frequency. For subcritical, supercritical, and critical point. In the right, the maximum frequency for different particle mass are plotted. We show that the peak of energy emission rate dependent on the value of the particle mass. The maximum frequency of the energy emission rate via the shadow radius for isobaric processor. The left we are traced at the we are plotted the RN at the S black holes massive without massive gravity, and right with massive gravity. We can say that one can reproduce the same phase transition for van der Waals system. To conclude, the shadow radius is a reliable tools to probe the thermodynamic phase transition in massive gravity. The maximum frequency actually reproduces the thermodynamic behavior usually described by the plan temperature, Hawking temperature and radius and reason radius, and the massive field derived from Wien's law once the mass excited by Hawking temperature. Thank you for you.
Thanks a lot, Mr. Hisham. So if you have any questions, please. Questions? No question? So we go to the other poster, to the fourth poster, which will be presented by Yunus Alaima online. Yunus, do you hear us? Okay, this piece is yours. Yes, you can. You can go.
Presentation done?
Yeah. We see your presentation.
Okay. Hello everyone. My name is Yunus Alaima. I am a PhD student studying black hole and Cartesian optical black hole, supervised by Prof. Ahmed Tassou. I am honored to present the Physical Energy Environment and Application Laboratory for the Discipline Faculty, Cadi Ayyad University. Before we start, I would like to extend my sincere gratitude to the organizing committee of the ICAY 2026 for organizing this wonderful event. Today, I am excited to present our work rotating regular black hole in string cloud background, thermodynamic and shadow. To ground our study, classical general relativity predict an inevitable space-time singularity, where the law of physics is break down. To resolve this, we use the model of a regular black hole. We resolve this via a new singular system core. Also, furthermore, when you look back at the early universe from the cosmic string, the model of cloud of string proposed by Newton described the matter might of an ensemble of one-dimensional relativistic string rather than traditional zero-dimensional point of particle. Our primary object is construct a rotational regular black hole and string immersed in string cloud and extract the phonologic observer of even horizon telescope. We start to form the spherically symmetric static metric developed by Santos, which combine two parameters, the logarithm pattern L0 and also the string density. and m is the mass of the black hole. We apply the Newman-Janis algorithm, but the ICAY modification to avoid antiphysics complexation, and we know our solution is origin function, with A is the spin parameter. And we showed the figure 1 as origin function, increasing the string density to 0, 1 to 0, 25, and this string density expand the outer horizon of the black hole. But now thermal stability, we calculate the Hawking temperature of black hole and the entropy, and we show this string density amplified total entropy, and also the height capacity of the black hole and the atmosphere energy. We studying the local stability of the black hole, showing in height capacity. For the stability height capacity role of aggregate second round phase transition, and the free energy stabilizes into metastable element, avoid total evaporation. Now, how does this theoretical constant manifest into distance observer? To find out, we simulate the black hole shoulder. So, mapping our results directly to observer the stability HT, our analyzer to affirm the two parameter. Still, the density act as a gravitational mapping, monocyclically increasing the shoulder radius, and the spin parameter slowly derive the asymmetrical shape distortion with the epsilon decrease, the DC decrease. For conclusion, the center 56 replaced by regular de-Sitter-like core, the same background induced a thermal stability of the black hole and enlarged the black hole shadow, provided a robust regular alternative to Kerr metric. For future and perception work, we can study of this model, the Cadi model, and gravity lensing, and also the observational constant fitting the parameter using the HTF data from 87 and Secretary A black hole. And thank you for your attention.
Lots of thanks, Yunus. So, any questions? No questions? So thanks a lot, Mr. Yunus.
Thank you, Mark.
And we wish you good luck in your work.
Thank you.
We go to the last poster, which will be presented by Ms. Mariam Tarmoussi.
Hello everyone. Today I'm going to present my poster, Is the Moon More Than Just Grey? So I will bring you to a journey to the moon where we look up onto the sky and we see this familiar silver orb, a world we often picture as entirely monochromatic, dry and fundamentally dead. But if you look closer, the moon is hiding a magnificent dynamic past. In December 1972, during the Apollo 17 mission, the very last time human beings set foot on another world, an astronaut and geologist, Harrison Schmitt, was exploring the rim of Shorty Crater in a Taurus Littrow Valley. And there, amidst the pale lunar dust, he saw something extraordinary, a vivid flash of orange. What he had stumbled upon was sample 74220, the legendary orange soil. It wasn't just discolored dirt. It was composed of nearly 99% of volcanic glass beads, ranging from 10 to 300 micrometers across. These tiny spheres were forged 3.7 billion years ago, capturing the fleeting moment of pure cosmic fire frozen in time. So, how do you get orange glass on a desolated world? Imagine the moon nearly 4 billion years ago, It wasn't silent. Great fountains of molten rocks were erupting high into the lunar vacuum. Spectacular fire fountains. As these molten droplets flew through space, the total absence of an atmosphere meant they cooled instantaneously. They quenched so fast that the crystal didn't even have time to grow, turning them into pristine glass. And the secret to that magnificent color is it's down to chemistry. High concentrations of titanium and iron trapped within the rapid cooling matrix give these beads their brilliant fiery hue. So they were buried for eons until a meteor smashed into Shorty crater, bringing them back to surface just in time for Apollo 17 to find them. Now, to truly unlock what these beads are telling us, we have to look closer than the human eye allows. I want to express my deepest gratitude to Dr. Ian Crowford, who kindly walked me through the remarkable process of how scientists analyze these precious samples today using polarized light microscopy. By taking a section of these glass beads, just 30 micrometer thin, far thinner than a human hair, where light can pass through, and passing polarized light through them. As you can see in the central image here, right there, scientists can map the internal crystal structures, trace exact mineral composition, and compare these orange glass spheres to black glass variants. It allows us to read the chemical fingerprints of the young moon. Why does this matter? What's its significance? Because these microscopic glass beads completely changed our understanding of lunar history. They've revealed that the early moon was far more geologically active than we ever imagined, holding trapped evidence of explosive volcanism and volatile molecules, including water, deep within the lunar mantle. Understanding these ancient fire fountains doesn't just tell us the story of the moon. It gives us a window into the fiery childhood of Earth, Mars, and the evolution of terrestrial planets across the universe. So to conclude, the moon is far more than just a grey rock. These beads preserve a remarkable record of ancient lava fountains. Locked within these tiny orange glass beads and is a breathtaking record of ancient lunar fire, preserved for 3.7 billion years ago, just waiting for us to read it. Thank you very much, and I'll be delighted to take any questions.
Thanks a lot, Maryam. So if you have any questions. No question? So it's okay, thank you a lot. Thanks again. So now it's time to go for the closing speech. So I invite Mr. Alexander. So for 5 minutes. Okay. This is yours now.
Thank you very much. Well, everyone, I think it's uploading. Okay, I will start anyway. So thank you very much for attending this conference. It was really a pleasure to hold it for the first time out of France. Thank you for your participation, for the good vibe you put it in all through this event. I felt like we built something, this edition, a community, some unity, some kind of link between each other. So I'm really glad we had the opportunity to do so. Moreover, I would like especially to thanks Professor Benrita and Professor Shukar for the implication, and the whole organization team, Mohamed and Ralph, for being able to convince us to hold the first Out of France edition here in Morocco, for your dedication, your time, your efforts. So I really want to extend a deep, warm thanks to them, and I think we can all thank them. Now I'm gonna just talk a little bit about the future, because, well, it's the end maybe of this edition, but we're not planning to end there. I hope
continue. Okay. First of all, I don't know if you've seen this amazing picture we got on the first day, but we were kind of happy to being able to close this ceremony with the same pic we open it with. Of course, a deep thanks to all the partners, but I just wanted to say, and if I don't say that, the communication team will go on my back because I didn't say that we have social medias, and those social media are, of course, for bits of advertisement, a bit for fun and a bit for science, a lot for science, of course, but also it's a way for you to grab the pic we took of you this week. This whole congress. If you want a special pic from you during your presentation, I think we'll be able to make it available for you. Also, on those medias, we have a lot of content throughout the year, and you will be able to know a bit more about next edition, because that's what is coming. Next edition. So of course we're gonna continue next year. I'm not gonna still say where we're gonna continue because I love having a little bit of secrets that spice the thing up. But we're gonna continue with the next edition next year and the year after too. So we're looking after universities and all participants and all countries that wanna host us next years. So if you're willing to do such, I think it will be a pleasure to meet you and to discuss that matter. I think Jamila and Hita could say that it was sometimes difficult, but overall kind of a great thing to have us here. And I just want also to do a little bit of more self-advertisement for the ICAY, because in the upcoming years we're gonna grow more and more, because it's the life of a congress and of a conference to just grow, and we need help in the international delegation too. We need help for organizing the communication, but also the general logistic, because there will be a lot of surprises and new events in the coming years. The ICAY will not be only the annual congress that you know now, but there will be other things that will be coming. So we need your help, we need your ideas, we need your energy, and we need your energy, your good vibes that you gave us all this week. So thank you very much for attending this congress this year. I hope you enjoy it, and I think it's not really over now because we have still the gala and the excursion tomorrow. So please enjoy the last hours of Congress, and thank you very much.
Thank you, Alex. Good afternoon, everyone. As we reach the end of our conference, it's my privilege to offer a few closing remarks. Over these 3 days, we have shared a rich and diverse scientific program. We have heard presentations covering many areas of astronomy and astrophysics. We had stars, variable stars to exoplanets, space weather, astronomical observations, instrumentations, lunar science, as well as citizen science. This diversity has made this conference a valuable meeting point for different ideas and perspectives. Over the past few days, ICAY has brought together participants from Morocco, France, Spain, and Senegal, united by shared passion for astronomy and space science. Seeing people from different countries, different backgrounds, and at different stages of the academic journeys, exchanging ideas has truly reflected the spirit of this conference. I would like to express my sincere gratitude to all our invited speakers. Thank you, Dr. Anders and Georgie. I thank also the other one. Thank you, Mr. Abdelrajid Ben Hida, Ahmed Dasso, Professor Aziza Bounir, Professor Michel Blanc, who were remotely with us. So thank you for joining here in person or remotely. Thank you for sharing your experience, your research, your knowledge, your ideas with us. My sincere appreciation goes to all the participants. Through your talks, your poster presentations, your questions, your discussions, you brought the energy to the program, and you played an essential role to making this ICAY or this conference successful. I also thank, so my sincere appreciation to the members of the international delegates, and a deep appreciation to the local organizing committee for their dedication and commitment throughout the participation and the preparation and the running of this event. So thank you very much for your help and for supporting us. I thank also our technical staff, Mr. Munaim, who's been here with us through the 3 days of ICAY and who's been helping us all of this period. All our volunteers and everyone who works behind the scene. Your contributions may not always have been visible, but without you, it were like your presence and your efforts were essential to the success of this meeting. As this conference comes to the end, I encourage you to maintain the connections you've made here. So please continue these conversations, exchange ideas between you, and look for opportunities to work together. So let this conference not be the end of our conversations and our discussions, but the beginning of new collaborations, new friendships, and new projects. Before I conclude, before I finish, may I invite all the organizing committee, all the members, to join me on stage. Yeah, the international delegate too. Yay, all of you. Yeah. Amar, Misal, please come. Yeah, of course. Yeah. Everyone who helped in making this conference successful, I invite you to come to the stage, please. And you, please. Yeah, Sufyan. Yeah, please. Yeah, sure. Karim, please, you too. Thank you very much for your time, for your support, and for your help. On behalf of the entire organizing committee. Yeah, welcome. So on behalf of the entire organizing committee, I'd like to thank all of you for your presence, your contributions, and the positive spirit you've brought to this 3 days. Thank you very much, and see you soon. Maybe we can, I don't know, we look forward to seeing you at the gala dinner. So please make sure to bring your ticket gala with you, okay? At 6:30 p.m. Okay? It's just in front of the door of this door, the faculty. Thank you so much for being here. Thank you very much. For tomorrow, for the excursion, so the bus will be here at